Well, I hope you enjoy your 45-minute nap initially. And also, this is a talk on flavor physics, but the flavor of breakfast seems to have won. So I will give you a brief tour of Bell 2 physics. I'll start with the why, explain why we're doing flavor physics in E plus E minus collisions, and particularly what Bell 2 is. And then I'll give some highlights. Initially, I will talk a little bit about the general methods that we use at Bell 2. And then I'll talk about several B physics measurements, which are really the bread and butter measurements of Bell 2. And then I'll talk a little bit more about things that are not B physics. And this is becoming ever more important at Bell 2. So this is some tau physics, some measurements related to the G-2 muon anomaly. And inspired by something said yesterday, I'll say something about exotic hadrons before describing the current status and the plans. So the why. I can use this, I think. So flavor physics has a very important role in the development of the standard model in general. And an example of this is early on, of course, there was this particle zoo discovered in the 50s and 60s, and then it was sort of made sense of by the eightfold way and the introduction of 3 quarks. However, there were still some unusual things happening. For example, for the long-lived neutral kaon, it was expected that it should be able to decay into 2 muons. And there were lots of theories about why this was possible and the rate it should happen. However, it was not seen. It was expected that it would be observed at some rate. Now, on the right side, we have our modern view of this in terms of a Feynman diagram, and it's a flavor-changing neutral current decay that only happens at second order in the weak interaction. And here it's written in terms of just those 3 light quarks. And this is how it would proceed. But the answer came because of the so-called Jim mechanism that predicted that there should be a 4th quark. So this is well before any observation of the charm quark. It was suggested that there should be one. And this would then lead to the suppression of such flavor-changing neutral currents. So using Cabibbo's quark mixing mechanism, you get the second diagram down here, which has the charm quark, but you pick up a minus sign from the quark mixing, and that leads to an almost perfect cancellation between these 2 diagrams. The only difference is the mass difference between the up quark and the charm quark. So what's interesting about this in the whole story of flavor physics is you're actually looking at a particle which has got a mass which is significantly less than the charm quark mass, except you're learning something about a higher mass scale. And that's generally the story in flavor physics, that you're always learning about higher mass scales by looking at lower energy phenomena. So similarly, an even bolder prediction came from Kobayashi and Masukawa when they looked at the 2x2 mixing of Cabibbo of the light quarks. Even before we'd seen the charm quark, they realized that you needed a 3rd generation to allow for the observation of CP violation in the standard model. So here we have the usual CKM matrix, which describes the weak coupling between quarks amongst the 3 generations. And the fact that this is a 3x3 unitary matrix, and once you've done the rephasing of the quark fields, you are left over with one irreducible phase, which allows for all the CP violation that we see in weak hadronic decays. So this was, again, a remarkable prediction, again, predicting particles at higher mass scales, this 3rd generation of particles which we had not yet seen, just from observations related to flavor physics. So, of course, there's many interesting puzzles in flavor, one of which is noted here is this very hierarchical nature of this magnitude of the elements in the CKM matrix. So it's almost diagonal, and as you move further away from the diagonal, you get smaller and smaller couplings. And unfortunately, the weak phase sits on one of the smallest couplings of all, so overall, the CP violation in weak hadron decays is quite small and can't explain the baryon-antibaryon asymmetry in the universe. However, it's still useful to probe CP violation. I'll explain a little more in a moment. And our principal tool for doing that is to reparameterize the CKM matrix in terms of one expansion parameter, lambda, which is the sign of theta Cabibbo. And then you can rewrite the terms in terms of this lambda, another parameter A, and then these two parameters rho and eta, which are related to the imaginary parts. So this is what's giving us CP violation. So this parameterization is the Wolfenstein parameterization is due to him. So now you exploit the unitarity in this. And what that means is you can combine the elements of the CKM matrix. And because some of these are complex, you end up with essentially three complex numbers in the Argand diagram. And because of the unitarity, they must sum to zero. So that's really just can be visualized as a triangle in the Argand plane. And the important thing to note about this particular combination is if you look at the magnitude of each of these three terms, they're all of the order lambda cubed. So that means that they're all three sides are roughly of the same length, and hence you get non-trivial angles in the triangle, and it's the easiest one to make measurements of that are interesting to test the Kobayashi-Maskawa mechanism. And this, and you see here also, when you write this in terms of these elements, because it's in using the third column here, it's got the beauty quark and all of this. So all the sides and angles of the unitarity triangle can be measured in B decays. And an example here is this angle beta, which you can relate together just in terms of rho and eta. So we know this very well. This is the triumph of the initial B factories, which I won't talk a great deal about. But you can measure it in different ways. Essentially, you're just measuring two parameters here, but you can make a whole set of measurements. So each of these bands here corresponds to one type of measurements. And you can localize the apex of this triangle, essentially measure rho and eta. It's sort of renormalized in a little way that it's called eta bar and rho bar here. But what one sees is you can use different types of measurements to do this. One's at tree level, where you don't expect much contribution from beyond the standard model physics. However, you have loop level diagrams, which actually give the most precise constraints from time-dependent CP violation, which I'll talk more about, and the mixing rate. And also there's still some contribution from CP violation in kaons. So what's interesting about this is because this is loop level, you can essentially explore potential new physics within these loops, and they actually constrain new physics up to very, very high mass scales by looking at this picture. So this is, again, the example of looking for beyond the standard model physics at very high mass scales. In fact, mass scales that are higher than those that can be reached directly at the LHC. So a goal of the next generation of B factories in LHCb is to make a comparable measurement in the tree level decays compared with the loop level, and of course, improve these over time. I won't talk so much about the tree level measurements in this talk, but it's certainly one of the primary goals. So why we do this at the Upsilon 4s? So this is a bottomonium resonance, and it's the first one that's above the mass threshold to produce a pair of beauty mesons. So the 1s, 2s, and 3s are below threshold, and they don't decay to B hadrons. So here we just have the total hadronic cross-section as a function of the invariant mass, and you see the lower mass bottomonium resonances here, and this is the 4s, which is a small peak above the continuum background, which is just light quarks going to E plus minus going to light quarks. But there is about a factor, well, this is about the cross-section for B mesons is around a quarter of the to light quarks. So it's a significant enhancement compared with elsewhere. So this is why we work at this point. Of course, we still have to worry about this background from light quarks. So there are advantages of doing this. One is these final states are very low multiplicity. You only have a pair of B mesons, you have nothing else. So this makes it very easy to reconstruct. And in fact, coupling that with the initial constrained kinematics from the electron-positron collision, we can make excellent measurements of missing energy. And I'll compare this to the LHC in a moment, but this is what we do very, very well. So we can reconstruct neutrals very well in this low multiplicity environment and missing momentum. Also, the B0 and B0 bar, because they're coming from this resonance, the Upsilon 4s, which is a known CP state, they come out quantum entangled. So this means that while they're both still there and they're in a quantum entangled state, so only when one decays do they oscillate freely, and this leads to very high tagging efficiency, which is important for time-dependent CP violation. And we also have a completely open trigger, so we essentially take 100% of all the BB bar events that are produced. There are, of course, disadvantages. There's a very well-known LHC experiment, LHCb, and also more and more CMS, particularly, and also a little bit Atlas are contributing towards flavor physics. And that's because at the LHC in proton-proton collisions, there's an enormous cross-section for BB bar quark production. It's 5 orders of magnitude larger than the electron positron. Further, they see all types of B mesons. We're restricted on B hadrons. Sorry, they have B baryons as well. We only have B0, B0 bar, B plus, B minus. And they also produce these with a very large boost in the laboratory frame because of the very high energies. And that allows for excellent time-dependent measurements because they fly longer distances. So that leads to better decay time resolution. So in our E plus E minus machines, we overcome this problem of the boost by having asymmetric beams. So the asymmetric beams that we have at Bell 2 and the earlier B factories allow us to boost the B0, B0 bar system and allow us to make time-dependent measurements and exploit that long lifetime of the B meson. So to talk a bit more about the detectors, there's a history here. Bell and Babar ran from so it's like 1999 for about 10 years, and they accumulated a data set just over 1 inverse Ataban at the Upsilon 4S, and they made many contributions to flavor physics. Particularly, they showed that the Kobayashi-Maskawa mechanism was certainly the one that described CP violation in the standard model, and they for that Kobayashi-Maskawa won the Nobel Prize. But they also made observations of many new phenomena, semi-tauonic B decays, direct CP violation in B physics, and many others, particularly advances in electroweak penguins, for example. So the idea of SuperKEK B and Bell 2 is to collect a much larger data set than that was done by the first generation. So it's essentially to increase the statistical size of the sample. And to do that, we have to increase the instantaneous luminosity of the accelerator. And the goal is to do this by a factor of 30 as to what's been achieved by the first generation. So at the moment, we have a world record instantaneous luminosity, around 5 × 10⁻34 inverse centimeter squared per second, but this is still a factor of 12 below the target luminosity. So I'll come back to this at the end. This is the main goal that we have experimentally, is to try and increase this luminosity. But we have already accumulated a significant amount of data. It's almost as much as Babar ever did in our run 1. And we use this so-called off-resonance data to study the properties of the light quark E plus E minus to QQ bar. So the detectors I won't talk about a great deal. You see it's not perfectly symmetric about the vertical axis, and that's due to this asymmetry in the beams. So we have the higher energy electrons coming in from this side and the lower energy positrons. Everything is boosted forward, but it has all the good things that you need in a general purpose detector: silicon tracking for vertexing, large radius tracking for good momentum resolution, particle identification to separate pions from kaons primarily, homogeneous calorimeter, crystal calorimeter of cesium iodide, thallium doped, and then we have a muon catcher on the outside. So this just also shows the upgrade that took place between Bell and Bell 2. We reused parts, particularly the very expensive calorimeter, and the return yoke for the solenoid, but virtually everything inside that was replaced otherwise. So I now want to talk about some highlights from the Bell 2 program. This is the vast majority of the talk. But first of all, I just want to explain how we make some of the measurements, because these things will come up a few times as I go through. So the advantage of E plus E minus is largely that you actually know what you're colliding together in the first instance, which is very different to the LHC, where you just have the parton distribution function and you know some gluons collided, but you don't know exactly what their momenta were in the initial state. So here we use the fact that we know exactly what the center of mass energy is, and it's very well known to a few MeV, to make particular kinematic variables. So one is the so-called beam constrained mass, where we take our candidate B signal and work out its momentum. And then we use the beam energy to construct its invariant mass. Now, if it's a true B meson, it will peak strongly at the known B mass, and then anything that's combinatorial will just follow this smooth distribution with this kinematic endpoint coming from the beam energy. However, if you partially reconstruct a B meson, you lose a soft particle that will also peak in this distribution. So you'll have a peaking background here. Or if you misidentify a pion as a kaon, so on and so forth, this will still peak in this MBC. So to separate this background, we also use the energy difference. So you work out the energy of the B from the B's full momentum, and then you subtract off the energy of one beam in the center of mass frame, and this should peak at 0 for a true candidate. Whereas if you miss a particle or you get the wrong mass hypothesis, it's offset. And again, the continuum follows a smooth distribution. So this is how we separate our signal from background kinematically. We also have to worry about this continuum background, but because our B mesons are produced just above threshold in the center of mass frame, they have very little momentum themselves. So when they decay isotropically through 4 pi. Whereas when you produce QQ bar, they're jetty and they go out back to one another and they form collimated jets. So we exploit the shapes of the events in the center of mass frame to differentiate between them. So we don't just use one variable to do this, we combine many, and we exploit the power of machine learning, and we can distinguish the topologies by putting them into some multivariate algorithm, which learns from simulation or sideband data how to distinguish signal from Monte Carlo. And then we often use the output of such a multivariate. So here is one from a boosted decision tree to separate signal from background. So the signal is here in pink, and the background is here peaking towards low values of this discriminant. And we can fit these distributions to help us extract the signal along with those kinematic distributions. So again, the B factory, because it's a low multiplicity environment and we have these constrained kinematics, we also benefit greatly from the fact that we can fully reconstruct certain events. In particular, if you have a B meson that's decaying to a charm hadron and a number of pions on one side, you will learn the momentum of that B. And then on the other side, you can look for states which are quite exotic or rare. So here is a forbidden decay in the standard model, which is lepton flavor violating. And it's a kaon, a tau, and a mu. So you can just reconstruct the mu and the k, and you'll have a missing momentum vector for the tau. And you can just use the missing momentum to get a distribution and see if there's a peak there for the tau. And this is a very powerful way of discriminating background in very rare decays. So this is so-called full reconstruction or hadronic B tagging, and we use this for certain measurements. The downside is the efficiency is very low, so the big boost in luminosity that we hope we'll get will really benefit many of these searches. But a few of the results I show will use this technique. And of course, again, as with everything these days, we use machine learning to help us. So there's machine learning on the tag side to get the best possible result. So moving to the bread and butter of our measurements, this is time-dependent CP violation. So how this works is that you have the B0, which can decay to some eigenstate, or it can mix and then decay to the same CP eigenstate. And in the mixing, they pick up one of the angles of the unitarity triangle, phi 1 or beta. And so there's a phase difference between these two paths. So there's interference, and hence you get some dependence on this phase. So what you need to do to make these measurements is to not only reconstruct your signal. So here I have the CP eigenstate. So these two leptons are coming from a J psi. So this is J psi K short. Then you have to tag the other B to know its flavor. So that's best done by using a lepton coming from semi-leptonic decay, but you can also use kaons and other properties of the event. And then this, because this depends on mixing, it also depends on the time between the two decays. It coherently evolves here, so your clock only starts when one of them decays. And then the remaining meson oscillates and then decays. So you need to know what it was at time here and here. So we use the tag for this, and we use the separation between the two vertices to get the time difference. And that's where we use the boost between the two beams. So this flavor tagging, again, is important. We use leptons, kaons, and we can look at the momentum of these other events in the event. And we've now used graph neural networks, which are more advanced multivariate algorithm, which better uses the correlations between the various observables that you see in the event. And we've actually improved our tagging efficiency by about 20% almost by using these new techniques. And we're now up to around 37%, which can be compared. This is almost an order of magnitude more than the tagging efficiencies at the LHC. Yeah, so this is, sorry, this is just telling you whether it's a B0 or B0 bar, essentially. So it's a charge of the B quark, essentially. R is just quality. Okay, so when you're down here at 0, you basically, it's tossing a coin to say whether it's a B0 or B0 bar. Here, you're pretty certain that it's a B0. Down here, it's a B0 bar. So, yeah. So again, these analyses are done in bins of this QR, because obviously all the information lies in these two bins at the end. Stuff in the middle's more of a control than anything else. So the first of the measurements is a time-dependent CP violation measurement of B0 to eta prime K short. This is interesting because it proceeds via a penguin diagram. So it's a loop, has access to beyond the standard model physics, potentially within the loop. And this can be compared to those B to J psi K short decays that happen at tree level. So if there's any new CP phase within this loop, it would show up here. And otherwise, it's exactly the same as what I described on the previous slide. And we've made a measurement using the full run one data. We have just over 800 events using 2 decay modes of the eta prime. And the eta prime, you see, involves photons in its final state. So that's excellent for Bell2 compared with LHCb. This is a measurement that's difficult or almost impossible at LHCb. And we, again, do all those things I mentioned earlier. We use the delta E, the beam constrained mass, and the continuum suppression variable to separate the signal. And then we use the time-dependent information to get this distribution of the CPA symmetry as a function of this time difference between the two decays, delta T. And you see this oscillation, of which its amplitude is related to sine 2 phi 1. So the result agrees with that coming from the tree level decays, but its precision, even with the smaller data set, is almost as good as the preceding measurements of this decay. So related now to the unitarity triangle, this isn't a time-dependent measurement because we don't have a vertex in this decay, but this is B0 to pi 0, pi 0. So if you look at our knowledge of the angles of the unitarity triangle, we now know beta and now gamma reasonably well. The one we don't know well is alpha, which is from this light blue sort of band here is constrained. And how you constrain alpha is to use a combination of all the B to pi pi measurements and isospin to remove contaminating diagrams with penguins. This was proposed by Corona in London a long time ago. But the weakest link in doing this method is measuring this B0 to pi 0, pi 0 decay. And that's the reason, is because it's got 2 neutral particles, which are hard to reconstruct. But of course, at Bell2, we can do this. So a new analysis has come. Now this is a 4-dimensional fit, which is used, same as before, delta E, MVC, and some continuum suppression. But we also use this flavor tagging probability, or the wrong flavor tag in this case, which is all equivalent. And we can use the separation power on event by event level to get a better estimate of whether it's a B0 or a B0 bar. And we're now making measurements that are as precise as those that preceded it. And by the final publication, we will have converted this to a constraint on alpha as well. So moving away from time-dependent CP violation, I will talk about our highlight result from the last year or so, which is K to nu bar. So this is an electroweak penguin. It can happen via these two diagrams in the standard model. It's third generation sensitive because it's involving neutrinos of all three generations. And it's relatively easy to predict in the standard model because there's no coupling between the initial and final state. You just have to worry about predicting the form factor of the transition of the B meson to the kaon. So there is an experimental challenge here. The branching fraction is small, and also with two neutrinos, you don't get any good kinematic constraint because you're losing two particles you cannot reconstruct in your event. So there's no peaking in kinematics at all. So we developed two methods to look at this. One is this traditional hadronic tagging, where you reconstruct fully a B on one side and then look for a single kaon on the other. And then an inclusive method was developed that exploits many features of the event, and again, machine learning to extract the signal. So in particular, if you look at these topologies again, the B's are sort of isotropic, the QQ bar back to back. But when you have two neutrinos from one of the B's, you get something that's in between. You have this odd track, lots of missing energy, and then one isotropic B decay. And if you look at an event variable such as sphericity, which is telling you how isotropically distributed the tracks are, you have continuum events are piled up towards low values of sphericity, B events up towards larger values, and then in between the red is the signal for this K nu bar. So by combining many of these types of variables, we can actually distinguish between the signal and the background. And when I say many, I really mean many. There are actually two boosted decision trees used, one with 12 variables initially, and then another with 35. The cascade increases the efficiency by a factor of 3. And then this is the classifier output in quartiles of the and quantiles of the efficiency. So this is the top 8%. So it would be uniform for signal and strongly falling for the background. And then you can fit this these distributions using templates to try and extract the signal. And there's one other variable used, which is the invariant mass of the neutrino pair, which you know reasonably well because of the constrained kinematics. The hadronic tag is much simpler. The additional energy in the calorimeter is a key observable here. Sorry. So this is unfolding the bins in Q squared against those in this BDT variable. There are 12 bins that are fit with templates. And this is how the signal would behave, and this is how the background would behave. The signal, of course, is multiplied by a large factor compared with the standard model. We use these profile likelihood methods, which include all the nuisance parameters from systematics in the fit. And we try and extract the signal. But of course, using such methods, you have two concerns. One is whether your signal efficiency is correct. Is the boosted decision tree well modeled? Is it well trained? And have you understood if there are any sources of background that you may have missed that could fake your signal? So the efficiency validation is done by using a technique called embedding, where we take a high statistics type of B decay. Here, it's again J psi to a charge kaon now for a B plus. Then we remove the information from the B decay and substitute in the signal. But everything else is real data. And hence it looks like a large sample of the signal. And with this, you can test the efficiency and the performance of these boosted decision trees. So here are the outputs of these two boosted decision trees. The points are the embedded data, and the Monte Carlo is the histogram. And you see there's excellent agreement to around a few percent. So we feel we got the efficiency correct, at least to a few percent. The backgrounds are very thorny, but again, we feel we're modeling things very well. This is a combination, a comparison of Monte Carlo and data, where you just take the kaon and look at combining it with any other oppositely charged particle in the event. And you see across most of the invariant mass range, you're having very good agreement between data and Monte Carlo. You see here the D peak, for example, and then there's the rho peak and other things down here. Sorry, that would be this is the rho, phi, so on, and this is just threshold here. So we feel we're reproducing the data very well in Monte Carlo. And we also use sidebands. So instead of looking for a kaon, we look for a pion. And again, we see the background and the data agree with one another very, very well. And there are backgrounds from K-longs, which we don't reconstruct, but again, we so could fake the neutrinos. But again, we feel we have all of this under control from detailed studies. So the final result here is for the inclusive tag, the red is the signal. So we see a clear B to K nu bar signal. And in the hadronic tag, which has lower statistics, again, there's some signal observed, but the uncertainties are much larger. So these are the two methods, and then we combine them together. So the combined result is that there's evidence for this decay, the first evidence for this decay at 3.5 standard deviations, and the branching fraction is significantly larger, almost by a factor of 4 than that predicted in the standard model, and there's a significant tension of nearly 3 standard deviations between the two. So we're following this up with many more measurements of B to K or K star nu bar. Work is underway. I can't say any more. Okay. Ask me in about 6 months. So K star tau tau was a more recent highlight. We presented this for the first time this year. This again, the third generation is the interesting part here. Many theories of beyond the standard model physics predict things going on in the third generation and not elsewhere. And it also correlates with other B anomalies. So semi-tauonic decays have been consistently high in their measurements at the B factories and LHCb. And this is the current, or not quite current, a few years ago, but it hasn't changed very much from these ratios of semi-tauonic to light leptons. And there are certain theories that predict great enhancements of this particular decay, orders of magnitude enhancement, if you can explain these B to C tau nu transitions with certain models. I think this is lepto quarks, but I can't quite remember. But in the standard model alone, it's very, very rare, 10 to the minus 7. But we use this B tagging, so we fully reconstruct one B on one side, and then we look for 4 tracks on the other side, or also additional pi zeros to make rows. And we use all these different tau decays to make the efficiency larger, and we exploit the fact there's lots of missing energy because of the 2 neutrinos coming from the tau decay, 2 or 3, well, more than, sometimes there are 3 neutrinos, sometimes there are even 4. So we use this missing energy, and again, because it's fully reconstructed, there should be nothing else in our calorimeter, and these are 2 powerful variables to extract the signal. Again, I'm afraid we bundle everything into a multivariate because that gives us the best power, but it leads to sort of rather boring plots. But we've improved the limit over Bell by a factor 2. We don't see anything. You would have heard more about it if we had, but this is our fit to the run 1 data, and we're setting a limit that's twice as restrictive to any one that went before. So we're starting to get closer to the interesting region for this decay. So moving away from B physics in my last 10 minutes, I want to talk a bit about tau physics. So this, again, third generation and very interesting. It's been widely studied in the past, and there are 185 different standard model decays of the tau if you look in the PDG. And this is, of course, very interesting for a lepton because you don't have any of this going on for electrons and muons. So it's a wonderful place to study the weak interaction. However, it's also a place where we may expect to see larger effects from new physics. So an example here is a tau to mu gamma transition, lepton flavor violating, which can happen in the standard model if an oscillation takes place within this penguin loop, which is extremely rare. So this is like at 10 to the minus 50. But many beyond the standard model theory suggest greater enhancements of this by many orders of magnitude. So to look for such decays and related decays such as tau to 3 mu, so you just imagine 2 muons coming off the photon here. And there are connections both to G-2 and to the B physics sector from these models, and to dark sector 2. So E plus E minus at the Upsilon 4s center of mass energy is an excellent place to do tau physics as well. So if you look at the cross sections here for different processes, you see the BB bar here is roughly 1.1 nanobarns. And then this slice in brown here is that to tau, so it's almost as large. So for every BB bar pair, we approximately get another pair of tau leptons as well. And we have this wonderfully clean environment with nothing else but the two taus to study them. So an example of how we've exploited this is to search for this tau to 3 muons. Should be accepted by JHEP now. So you look on one side for a tau going to 3 muons, which is a very distinctive signature. The other side you try and tag to make sure it's a tau-like event, not combinatoric. And again, we use a multivariate for the tagging on the tau side. And then we use two kinematic variables on the signal side to extract the signal, or the search for the signal. So there's the invariant mass of the 3 muons, and then the energy of the 3 muons less the beam energy creates a delta E-like variable. So this is this two-dimensional distribution here. The boxy regions are the sidebands, which are used to do an empirical derivation of the amount of background we expect in the signal region, which is this sort of egg shape, which is oriented like this because there's a correlation between these two variables. So we estimate the background, which is expected to be around half an event. Unfortunately, we don't see anything, which you see from this projection. There's only one event within the signal region, but we set the world's best limit on this decay to around 2 times 10 to the minus 8. And this is reaching a level some models predict up to about 10 to the minus 9 or even higher for these types of decays. And this is an area of great competition. LHCb and CMS are in this 10 to the minus 8 region as well. So penultimate physics measurement I'll talk about is related to G-2. So a few years ago, there was a lot of excitement because the measurements of the muon G-2 were in disagreement with the theoretical prediction. And the theoretical prediction uncertainty is completely dominated by this so-called hadronic vacuum polarization, which is this higher order correction where you have a blob here, which is hadrons. And then they go back to a photon, and this alters the value of G-2. Now, since then, there's been lattice work, which has moved the prediction much closer to the experiment. And then there was a measurement of the hadronic vacuum polarization inputs from the CMD3 collaboration in Novosibirsk, which is again in agreement with the lattice and almost in agreement with the data. So this is very, very confusing. So what we need are more measurements to better estimate this hadronic vacuum polarization. So when I say measurements to work out this quantum correction, what I mean is that you can use the fact through dispersion relations that you can relate together that rate in the hadronic blob to E plus E minus to hadrons. Essentially, you're looking at the photon going to hadrons in the blob, and that can be directly related to the cross-section. Again, we normalize it by the cross-section to E plus E minus to mu mu. So this is this R ratio, and you have a kernel function from the QED. And what you see is there's a 1 over the center of mass energy. So the low center of mass energy stuff dominates this prediction for the hadronic vacuum polarization. So here, as a function of the center of mass, is the total hadronic cross-section with the various contributions. In yellow is pi pi, which is the dominant one. But in dark blue, the second largest one is 3 pions. And to the uncertainty on the prediction for the hadronic vacuum polarization, it's pi pi that dominates. But the next one at 15% is the 3 pions. Unfortunately, we don't have a pi pi measurement yet. We certainly are working on that, but we have done a 3 pion one. So for the 3 pion hadronic cross-section, we use what's called the ISR technique. So you reconstruct the 3 pions and an ISR photon. So you then scan a range of invariant mass. So what we then look for is essentially you have the 2 pions, 2 photons, and then you fit the 2 photon invariant mass to get the pion, neutral pion piece. And that's what you see with the points here. There is a small background, which is all constrained from sideband information. And this allows us to measure the cross-section, which you can then factor in to estimate its contribution to the hadronic vacuum polarization. So our measurement is here in the in the gray bands, and the earlier measurements are shown in yellow, orange, and blue from Babar and the Novosibirsk experiments. We're in slight tension with Babar, which is the most precise measurement in orange. We're about 2.6 standard deviations. Interestingly, our result pushes the value of the hadronic vacuum polarization closer to the measured value from the direct measurements at Fermilab. But of course, this is the precision here is limited because of our knowledge of the generator. This is higher order radiation and the pi zero detection, which is so these contribute such that we have about a 2% overall uncertainty on this measurement. But this is an interesting first contribution that we have to this program, and it's important to sort out what's going on with the G-2, as many of you know. So the last measurement, inspired yesterday by Murthy talking about the novel ideas Rajaji and others had in the 60s about non-conventional hadrons. There's, of course, been an explosion in the last 20 years of the number of hadrons. The number of particles discovered at the LHC is not one, it is about 100 and something, with all the different spectroscopic states that have been found, particularly by LHCb. I'm not sure if it's quite 100, but it's very high now. So we've used our old Bell data to look at upsilon 1s and 2s. So we took some data lower than the upsilon 4s, and we will do that in the future at Bell 2. And because these decays are OG suppressed to go to hadrons, already been observed that there's enhanced baryon production, which is lots of quarks in the final state. So maybe you can produce pentaquarks here. So we looked at inclusive production of J psi lambda, and then interrogated the J psi lambda invariant mass, and this is what you see here. And what you see is a peak at around 4.45 GeV. And this is consistent with a previous observation of a peak in a J psi lambda distribution coming from baryon decays at LHCb, B baryon decays. So we see evidence just over 3 standard deviations. And if we don't constrain our mass to that seen by LHCb, there's a 4 standard deviation local significance. So this is interesting because this is the first exotic state seen in the 1s, 2s decays, and also tell us something about what these exotic pentaquark states might be, given the different production mechanisms. All right, so to conclude, I should tell you about the future. And what I've been showing so far from Bell 2, a little bit from Bell also, was taken between 2019 and 2022. And this is where we achieved our world record. This is the instantaneous luminosity here. And we had a long shutdown where we installed a new pixel detector. And there was also a lot of work on the accelerator to try and improve its efficiency and combat beam backgrounds. So we restarted earlier this year. Our instantaneous luminosity went up to what we had before almost, and the PXD2 was working well. Here I show the impact parameter resolution as a function of the transverse momentum of the track on a logarithmic scale. So if you have a hit in the closest layer in the pixel detector, you get better resolution. Second layer, you get slightly worse. And if you don't have any pixel hits, it's much worse. So this is really important for all our time-dependent measurements in the future. However, we're not getting up our luminosity to the level that we'd like. We want to be running it at 10 to the 35 and above, certainly in the short term. And there's a reason for this. We are having a lot of instabilities in the beam. Something called sudden beam loss happens. And this can lead to very large doses in the detector. Doses so large we quench some of the superconducting magnets. And this is hampering any increase in luminosity. And in fact, 2 of these losses damaged our new pixel detector. We lost 2% of the gates or the pixels because of this. So we've actually turned the pixel detector off as a precautionary measure at the moment. And a lot of the run 2, we haven't collected much data because it was largely for machine studies. And that's been good because we've understood a little bit more about these losses. They seem to be related to dust in the beam pipe. So over the summer, we've done a lot of work to try and remove the dust. And also we've made gravity our friend by flipping over some bits of the beam pipe. I can tell you more about this if you're interested. And we'll start again in a few weeks and we'll see if this has improved our beam stability and that we can move to 10 to the 35. So this hasn't been great news this year, but run 2 is long. We intend to run probably to the end of 2028 or later. So we still have several years. And if we can reach around 2 times 10 to the 35, we'll accumulate several inverse autobahns of data, far more data than any experiment previously. And then there's a lot of work going on for an upgrade program, which would allow us to get to this final luminosity of 6 times 10 to the 35. And this has a framework CDR now, which was released in June this year. So there's a long, bright future ahead going into the next decade. And hopefully, if you invite me back to the next TAP, I'll tell you more. So that's my conclusions. I think I'm almost out of time. So I've given you a brief tour of the flavor program at Bell 2 and a little bit more. We're doing lots with the current data we have, and we hope we'll have results with instantaneous luminosity of 10 to the minus 35 inverse centimeter squared per second before too long. Okay, thank you very much.
It's exact time. Thank you. Okay, now for questions. People who, yes, Indu.
The 3 pi, yeah. The next, you had the slide of the comparison between no, before. That one, yeah, that one. Yeah, the sigma other by Bell. This comparison with Babar, I mean, they're not even the orange lines are, at root S smaller are above 0, and then at root S. So it's not, I mean, is it calibration? Is it?
So, yeah, so this is.
I mean, what happens at 0.784?
So the omega happens there.
Sorry?
The omega peak is there.
So background subtraction?
So okay, I missed several steps in this analysis. So background is unlikely to have much to do with it. So this is a logarithmic scale, so you're already down by 2 orders of magnitude on the background. And this dominant background that you see here, the yellow and the green, this we calibrate off data. So we're pretty confident we've got this right. So you can make sidebands which have these data and we've got the rates right. What's tricky is the omega line shape and the unfolding that we do to get to this actual distribution of the cross-section in bins of the square root of S. And there's some suspicion that one or other of us is not necessarily doing the unfolding correctly. However, we've done many checks, so we're confident in what we've done.
Okay.
So,
no, at least yours is moving smoothly from below 0.78 to above 0.7.
but you know, this is normalized to our results, so we're cheating a little bit here. So we make everyone else look bad, right? Because we're the ones sat here at. So this is relative to our result. So, and there's also issues potentially with the pi zero efficiency as you move along in invariant mass, because the pi zero momentum in these bins is different on average. So if there's some issue with low momentum pi zero reconstruction, which is not fully calibrated, this could lead to this kind of effect as well. Because this is very close to the 3 pion threshold. So your pion is very soft. It's being boosted to some momentum against the ISR photon. But again, this requires some further investigation. But we've done a lot. We're a live experiment. No one from Babar in this room, right? So they're doing this measurement, having been shut for nearly 15 years. So the level of scrutiny it gets compared with something from a live collaboration is significantly less. However, the people that do this are very, very good. So I don't know. No.
Thanks.
We have lots of members from Babar on Bell too, so we have good interchange. And in fact, the Orsay group that did this measurement, some of them are now members, so we can talk. So it's okay.
Okay.
In addition to this PCS, there are these PC states that were also observed by LSCB. Is that possible to say something about them? There are 3 of them now.
Yeah. So there are ongoing searches now. The LHCb states, right? some have been observed in baryons and some have been observed in B decays, right? Of the pentaquark states. So the problem that we have is statistics in the B decays. We will certainly look, but it's unlikely. These were fully hadronic final states, and we don't compete very well. Fully charged track final states, and it's hard for us to compete in terms of numbers. But we will look to see if we get some signal.
Sorry, Bell discovered also these 4630 and 4660 Y states,
Yes.
which were actually claimed as baryonium kind of levels by some theoretical studies, like baryon and anti-baryon. Is there some efforts or some ideas to identify whether they are actually composed of baryonium kind of things or tri-meson kind of systems or something like that? I don't know.
Yeah, so there will be an
Thanks.
active program to measure the Y states. So these were studied largely in ISR events. So currently, because we don't have so much data, we haven't looked. But once we have more data, we will start using that sample to try and investigate all these different models of whether they're molecular, tetraquark, whatever you just said about the baryon system. Yeah, I'm no expert on the spectroscopy. I shouldn't have mentioned. I only mentioned it because Murti mentioned it yesterday. But no. But it's Bell too started all this renaissance. Bell started all this renaissance in spectroscopy by the X3872, and since then there's been this explosion of all these new states. So yeah, we know there the baryon meson picture is no longer enough. But, so where we will complement LHCb is we can do isospin states with pi zeros and neutral kaons. However, whether our statistics will be enough, we're not sure yet. Okay.
Maybe you said it, but on this thing, if you take your value of mu,
Yeah.
how does it look with respect to G-2, the experimental?
Yeah. So if we take ours, it's a 10% shift. So here you're looking at whatever 2.5 units. So it would move up to about here.
Oh, so it moves in the right.
It moves in the right direction.
Okay.
But pi dominates everything. So the current situation is you have this one measurement here, you have a Babar measurement around here, and you have two Chloe measurements here. And that's what's driving the position. And yeah.
Can I ask one more?
Yeah, please.
So you showed B plus to K plus nu. Is B0 to K0 nu doable at all? Or
K0 to nu?
B0 to K0 nu.
Yes.
Is that doable? Is that already measured or no?
So exactly the same techniques can be used. You just substitute the charge kaon for a K short. Problem is you get at least a factor of 2 reduction because you don't have the K, you have the K short, K long. Then you get another 30% because you will look for the K short in pi plus, pi minus, and pi zero, pi zero. So the statistics are lower. So it'll take more data to see a significant signal, but it's certainly there. The mode that's of great interest is the K star nu bar, because that's a different spin as well. So if there's something, it's possible that there's a intermediate state there that's then leading to the nu bar. That would have different behavior given the different spin structure. So K star, K0, S, we even have a fully inclusive XS nu bar. All these things are being looked at.
Thank you.
But I can't say anything else.
For the kinematics, so thanks. The nu always comes in the same direction. The two nus are boosted in the same direction always.
No. So
that's, I mean, yeah, just that you had a little picture. Yeah, that little cartoon had the neutrino always. No.
So, that's just how it was drawn. But
Okay.
in principle, you could have a zero.
So you may
momentum.
have no missing energy at all if the kinematics is right,
No, you have
or no missing PT at least.
no missing momentum.
Momentum,
It's
yes,
possible
it's possible. Okay.
because they could. Well, not.
No.
Yeah, no, you'd have overall missing energy,
Yeah,
but not net missing momentum.
correct. Yeah.
So that's all included.
Okay.
I think in
So
the
if-
backup, sorry, I can,
Okay,
I
sure,
can
sure,
help
yeah.
you. I think in the backup I have. Yeah. No, that's the control mode. And this is where it hangs. I don't know why. Okay. This is the one I want. Okay, so this is the reconstructed invariant mass of the two neutrinos. Okay.
Okay,
So you see the signal is distributed in this way. This template is standard model distribution.
okay,
So it goes down to very low invariant mass and can go up pretty much so that the k-on has very little. But our efficiency drops off because we need the k-on to identify the signal. So this corresponds to our efficiency is falling. But this is the distribution that we have.
No, but what I was really thinking of was you can't tell whether you have one neutrino, two or three, right?
No.
Okay.
Well, if you had one missing particle, that would be a peak in this distribution.
Of course, that's true. Yes.
So we can tell one from two, but we can't do two from three.
Okay. Yeah, good. Thanks.
Okay, thank you. Okay. There are no further questions. Let's thank the Jim for fantastic talk. Our next speaker is Abhijit, and he'll talk about hunting for primordial black holes through Lyman alpha forest. Black hole dark matter, sorry.
Am I audible?
Yeah, 15 minutes, I'll tell you 2 minutes before.
Okay, thank you. Okay, good morning, everybody. So at the outset, let me thank the organizers for giving me this opportunity to present my work. So I'm going to tell you how to hunt primordial black holes in the Lyman alpha forest. And this is based on a recent work that just appeared in arXiv just last week. So feel free to go through the paper. And let me first acknowledge people with whom I have done this work. So this is done with Ranjan Laha, who is sitting at the last row, who's my PhD supervisor. Priyank Parashari, who is now a postdoc at the University of Southern California. And Akash Kumar Saha, who's a fellow graduate student at the ISC with Ranjan. Okay, so let me first give you a bird's eye view of what I'm going to tell you about. So this should, orient you, where we are going. So if dark matter is made of primordial black holes, and if those primordial black holes emit Hawking radiation, the Hawking radiation can heat up the intergalactic medium a little extra over and above what other sources would do. Now you go and measure the intergalactic medium's temperature. Somehow you measure it, and there are two possibilities. If you find that the intergalactic medium is heated up a little extra over and above your expectations, then you can go and ask the question whether that extra heating has been caused by the primordial black holes. But if it has not been heated up extra, but evaporating primordial black holes would have heated up, so you can just constrain the primordial black hole abundance. So this is a single slide summary of my talk. Now let's get into the details. So this is, I'm sure almost everybody in this room has seen this picture hundreds of times. This is the pie chart of our ignorance. And around 27% of the energy density of the universe today is unaccounted for. Gravitationally, it behaves like matter, but we don't know what it's made of. And there are various possibilities. One of the possibilities is that it's made of primordial black holes. So what these are? So these are just black holes that were formed very early in the universe. The most popular mechanism of their formation is that the very high matter over densities would have directly collapsed to form black holes. But there are some other mechanisms for their formation also, several of them. And depending upon the mechanism, they can be formed having a wide range of masses, and they can have non-zero spins also, technically. Okay, now a little more about them. They would be moving non-relativistically today, since they redshift just like matter. And except for gravitation, they would have hardly any interaction with the baryons. And for high enough masses, they could be stable over cosmological timescales, and they would contribute to the baryonic matter density today. So of course, this smells like dark matter. And yes, there are models which predict that they form in the right abundance to form a substantial part of the dark matter density today. So it turns out that all black holes have a temperature. This is the famous result proven by Hawking. And so this is the temperature that's associated to every black hole. And the important thing to note is that the temperature of a black hole is inversely proportional to its mass. This is when the black holes are not spinning, the non-spinning and uncharged case. And Hawking tells us that these black holes will evaporate in the sense that they will emit all standard model, and if there are BSM particles, all those particles would be emitted with a spectrum. And what the spectrum looks like? So it is mostly a black body spectrum, except for these factors. And these are called the gray body factors. Now they come into picture because a black hole, the space-time is curved close to the horizon of a black hole, it's exerting gravitational force. And when a particle is Hawking emitted, so the wave function of the particle experiences scattering in the curved space-time of the black hole. So basically, the particle can be re-emitted back into it, can be attracted back into the black hole. So we have to account for these factors also. These are called the gray body factors. And since it's a scattering problem, they have to be evaluated numerically. And this we did by using this publicly available code called Blackhawk. And yeah, so let me tell you that this expression for the spectrum is valid only for the black holes which are not spinning. When they are spinning, then there's slight change in this factor, and this gray body factors also start to depend on the spin of the black hole. So yeah, but we calculated these gray body factors both for spinning and non-spinning black holes using the same code. Now, what Hawking radiation does to the intergalactic medium temperature? So since we are injecting some possibly high energy particles, and neutrinos would also be emitted, but they are not efficient at depositing their energy. And we need to consider only photons and electrons and positrons which are injected into the intergalactic medium. And it turns out that when these particles are emitted into the IGM, they, several processes happen, atomic as well as, so the heat is deposited over cosmological timescales, and we have to actually, work out what happens to the temperature of the intergalactic medium. So what we have to do is we have to solve these two schematic equations. So the rate of change of the temperature of the intergalactic medium is given by whatever would be if you don't inject anything extra, just the adiabatic expansion of the universe. And if you are injecting extra energy due to primordial black holes or anything else, and because at some point stars also start to form in the universe, and they would also start to inject photons into the intergalactic medium. So this is the rate of change of temperature due to reionization. And similarly, there's this differential equation for the ionization fraction of the gas in the IgM, because all this energy injection due to the primordial black holes as well as reionization sources, this can ionize the IgM also. And these two are coupled differential equations that have to be solved in an expanding universe. So this is done using another code, publicly available code again, called dark history. So we use these two equations. We solve these two equations using dark history, assuming that this extra exotic energy injection is coming from the spectrum of the primordial black holes. Now we have to go and measure the temperature of the intergalactic medium somehow. We know, we should know that how its temperature should change in the presence of evaporating black holes, but how do we go and measure the temperature of the gas? So we make use of this Lyman alpha transition, which is the most ubiquitous transition in the neutral hydrogen atoms. This is just when electron transitions between the principal quantum number 2 and 1. Yeah, so because of this spin orbit coupling, it's actually a doublet. So yeah, these are some properties of this line. So how does it help us? So suppose there's a distant quasar at some high redshift 6 or something. So quasars have a very broad spectrum, as the light from the quasar comes to us, so if there are clouds of neutral hydrogen in between, I say clouds because reionization also starts at these epochs, and hydrogen, in some regions the hydrogen gets ionized, and in some regions there are clouds of neutral hydrogen. So as this light passes through the clouds of neutral hydrogen, because it gets redshifted as it goes along, we will see these absorption lines due to the Lyman alpha transition. And it turns out that the width of these absorption features contains information about the temperature of whichever cloud is causing that absorption line. So by looking at analyzing this spectra, people have been able to, find the temperature of the intergalactic medium as a function of redshift. So this is just to show you how the spectrum actually looks like. Yeah, just focus on this lower spectrum. So as so this is a quasar at redshift 3.62, and as its light come to us, it sees all these absorption lines due to the various clouds that are, in the intervening region between the quasar and the observer. So now what are the results? So on the horizontal axis, I have the redshift, and on the vertical axis, I have the intergalactic medium temperature. Now all these data points are the measurements of the intergalactic medium temperature using the Lyman alpha spectrum analysis techniques. So these different colors are due to the different data sets that we use. And yeah, so focus only on this, don't focus on this faded data points. This is something that were actually present in the data set, but we neglected them because either they were in tension with some other point, for example, this one. And in this region, we don't take into this because when we solve the temperature and ionization coupled equations, we have to keep in mind that I showed you the ionization differential equation also. That was assuming that there's only hydrogen in the intergalactic medium. Now, below these redshifts, helium also starts to get ionized. And so we don't know how to handle it. So we work only till here. Okay, so these are the temperature measurements. Now, what is this red curve? This red curve is the temperature of the intergalactic medium that's predicted by some reionization model. Now, we don't completely understand the processes of reionization. There's wide uncertainty in how it actually proceeds. But this curve only shows that there can be a reionization process which completely explains all these temperature data points. Which is to say that actually we don't need primordial black holes to explain these temperatures. And hence, we don't claim a discovery of these black holes. We can only put a constraint on their existence. And this is to illustrate what happens to the intergalactic medium temperature if we have a primordial black hole dark matter. So these primordial black holes, each of them with mass 10 to the 16 grams, contribute only this 5 times 10 to the minus 3. This is the fraction of the dark matter density that's contributed by primordial black holes of this mass. Now, if we put these also into the mix, they would inject extra energy by Hawking evaporation over and above the reionization energy that's injected. And then the temperature as a function of redshift would look something like this, which means that this model is ruled out. So we carry out, this, we compute all this for various primordial black hole masses as well as the various densities, energy densities of the dark matter that it should be contributing to. And we get constraint plots. So on the horizontal axis, I have the mass of the primordial black hole. On the vertical axis, I have this parameter FPBH, which is just the fraction of the dark matter density that could be contributed by primordial black holes of this particular mass, assuming a monochromatic mass function. That is, all the primordial black holes are given by this mass only. There's no distribution. And so these are the constraints that we obtain. So what are these bands? So this red colored band that you see on the top, this is plotted assuming that the reionization sources are not heating up the intergalactic medium. And hence this is very narrow because then we completely get rid of the uncertainties associated with the process of reionization. But this blue colored band, this is when you assume that there's heating due to reionization also. And hence there are uncertainties associated with that process. Hence this band is a little broad. But these constraints are weaker, the one above the top, this red colored band, but they are very robust because whatever happens to reionization, these are not affected at all. And yeah, this is for black holes which are spinning. So their dimensionless spin parameter is equal to 0.99. And this is the exact same plot, which is for the black holes which are not spinning. So yeah, these are the constraints that we obtain. And both of these figures, these other lines show the constraints that are obtained by some other techniques. So, but yeah, this is the first time that these Lyman alpha measurements have been used to put constraints on the existence of primordial black holes. So yeah, this is all I had to say. I would just summarize that primordial black holes are black holes that could have formed very early in the universe. And Hawking evaporation of these black holes could lead to direct and indirect consequences, giving us the only way to search them because these are very light. So there's no other way to look for them. And Hawking evaporation spectrum, we computed the Hawking evaporation spectrum and utilized it to calculate the evolution of the intergalactic medium's temperature. And the temperature of IGM has been measured by people using Lyman alpha spectroscopy. And just by comparing the temperature evolution of IGM, assuming primordial black holes existence with the measured temperature, we can put limits on the existence of these primordial black holes as a function of what fraction of them can contribute to the dark matter density observed today. Thanks.
Okay. Are there questions? Yes. Yeah, okay.
Can you explain a bit more how you arrived at the conservative constraint, which was not dependent on the reionization model? I couldn't understand that part.
Okay, so see, you're talking about this versus this, right? So it turns out that, see, this is obtained by just using the free electron fraction as a function of redshift that we directly get from Planck. But the T dot term in this differential equation, yeah, this is switched off. Whereas in this, for example, this, this. So yeah, there are three colors. That's a bit confusing. That's just an artifact of the, how Matplotlib plots these colors. But the broader thing, we have that T star dot term switched on also. So that has a lot of uncertainties, which, astrophysicists tell us and we just take them as.
So could you just go to, I think, slide 14 or 13? I know 15. This one with it's when you discard data, I could make another choice and say discard the green points.
With this one?
Yeah.
Yeah, okay.
So did you try choosing a different data set, or even how bad is the fit if you keep everything?
No, I'll tell you. So the reason that this is discarded versus this is that if we take this, we get conservative constraints. If we had simply used this, our constraints would have been much stronger. So just we are just trying to be conservative in our limits. For example, so the temperature of this point is lower, right? So
yeah, I don't like this terminology of conservative. I consider myself a liberal, but I understand why it's done. But
Yeah.
I think it's important information because clearly I agree those points are in tension. What are the dominant uncertainties on these measurements that are going in?
Yeah, so there are several of them. So first of all, there's uncertainty that's come directly from the fact that how well you can resolve all this, lines that in the spectrum. And yeah, secondly, it turns out, that to infer these temperatures, you have to compare these, you have to generate mock spectra of Lyman alpha forest. And that is done using simulation. So the simulation themselves come with their own set of uncertainties.
Okay, it's interesting. Thank you.
if you keep the faded dots and remove the dark green ones, and you take 60% of your green line, then it will go through all your data points.
Sorry, I didn't understand.
You have your, what is it called? PBH with photo heating model. Look at
Ye-
that green line, right?
yes,
Because
yes.
it's all green. I can't help you. I mean, so if you just lower that by exactly 60%, then it will go through all the points except the green dots.
That's called cooking up.
Sorry? So I mean, it's like little dangerous to kind of decide, huh? Please, I would be very happy.
Laha.
Can you just pass the-
Sorry, Abhijit knows this, but let me repeat. So we talked to lots of, at least Prakash Gaikwad, who is a Lyman alpha expert. He has done some of these things. We asked him why is this difference? Even he does not know this. So I think this is why this redshift 6.5 is doing weird things. As far as we know, we also asked, I think Vikram Khaire, I think he also doesn't know the answer. So I think people who have done these measurements, they don't know the answer. And
Yeah,
that's
I
why,
don't know whether this is correct or this is
yes,
correct.
nobody knows that answer.
We are choosing what gives us the conservative limits.
And if you see the simulations, see as he showed, there's one solid line and then there's dotted and dashed lines. They are sort of the envelope. All of them go through everything. And then we are sort of stuck with, we don't know what to do. And then according to Prakash, if I do new physics, the best thing is to do the conservative case and just move forward. Yeah, but good. But you see, yeah, I take your point. So we can discard this redshift bin, but but higher redshift has more dark matter density, which should help us. So yeah, in some sense, we could have just discarded that one thing, but there are two other things. Yeah,
It's tricky.
yeah, I agree.
So we have exactly the same situation with G-2 and
Yes.
this cross section. At the moment, we do nothing with them because we can't average
Yes,
them. We
yes.
have to figure out what's wrong.
Yes, okay, thanks. Yeah. So,
I have a small question. The primordial black holes which you have, the masses are much, much less than the sun's mass itself, right?
Yes.
Probably it is, the
Yeah,
size.
these are the masses.
Yeah, the size will be too small.
Yes.
Is it reasonable to consider, because people consider slightly higher, at least sun's mass?
No. So see, yeah. So, you're talking about astrophysical black holes, but yeah, these can be as light as you want to. In fact, this lower limit comes also into the play just because these primordial black holes of these masses would have already evaporated away. But technically, if you go to the primordial black hole formation models, they can predict, very small black holes also.
Okay. Okay, thank you. Last question.
Sorry, I don't understand. So this, what is excluded here? Is that only the blue band and
No.
everything
So
above?
all this region is excluded. So
Okay.
the line above which everything is excluded is uncertain depending on what you do with your reionization. But for example, this region is certainly excluded. And here you have to, do some reionization modeling to exclude this region. So anything that's above this line is excluded. So for example, a primordial black hole of 10 to the 16 grams. So these black holes cannot contribute more than, let's say, 10 to the -4 of the total dark matter density.
So then why is there a dark blue band?
Yeah,
Why is
that's
it not-
because of the uncertainty in the reionization processes.
I see.
So reionization T star dot term that I showed, this term is not known at all. I mean, yeah, there's a very, the uncertainty in this term is
Okay.
huge.
Got it. Yeah.
Sorry?
When you say ruled out, to what confidence level? I mean, 95, what have you
Yeah,
put
these
in
are
there?
95.
95, okay. So the band will just mean that you're around 95 by a little bit.
Yes.
Okay, thank you. Let's thank the speakers again. Next speaker is Sayantan. Understanding the role of chiral symmetry. The QCD phase diagram. Thank you.
Hello, good morning, everyone. So I first begin by thanking the organizers for giving me an opportunity to speak in this conference which is dedicated to the memory of Professor Rajashekaran. And Professor Rajashekaran, as I had a fortunate time to have interact with him. I had an overlap of 5 years with him. And he, as Murthy said, he had a very wide interest. He used to keep on asking me about the recent developments in lattice QCD. I discussed some of it. And it is a pleasure to share with you some of the results from lattice QCD side in this conference, which is dedicated to his memory. So I will be talking about a specific topic in finite temperature and density QCD. And then there is another talk by Tanishq, who will talk about hadron spectroscopy, exotic hadrons in the heavy quark sector. And also there are posters by Bhavani and Navdeep. You must have already seen them. So by discussing about the recent results in lattice QCD, and we pay a tribute to Professor Rajashekaran. So my topic today will be understanding the role of chiral symmetry in the QCD phase diagram. And why is it important? Because it is believed that there was a QCD phase transition which happened at very early on in the evolution of the universe, about 10 to the power -6 seconds after the Big Bang. And this QCD phase transition is very important because it accounts for almost overwhelmingly large amount of the visible matter that exists in the universe, more than 99%. So all the substance that is made up of the visible matter is made up of hydrogen, helium. All of these owes their existence to the QCD phase diagram. So I took a plot from the recent website from CERN about the QCD phase diagram. So here on the y-axis is the temperature and the x-axis is the baryonic density normalized by the D0, which is the, I think, the nuclear saturation density. And the important point I would like to convey here is most of the phase diagram is unknown. So all these yellow bands and everything, these are all unknown. There is no first principles calculation of the phase diagram, not yet known. Studies from model quantum field theories which have same symmetries as QCD tell us that there may be a first order phase transition at high baryon densities and low temperatures. And what we know definitely from lattice studies is this region of the phase diagram at high temperatures and relatively smaller baryon densities. Smaller meaning it's much smaller than the nuclear saturation density. So it's nuclear saturation density, we are somewhere here, and saturation density plays a role in this region. And the primordial universe, the trajectory that happened during the evolution of the universe must have gone through this region. And we know for definitely from lattice studies that there is a phase transition from a phase of color neutral hadrons to a phase where there are quark and gluon-like quasi-particles, or the color degrees of freedom are liberated. And this phase transition happens not, it is not a true phase transition, but it is a crossover. And we know the crossover temperature very well. And there are two different mechanisms that give rise to this whole phase diagram here. One is called the chiral symmetry breaking, whose experimental signature is that we see pions which are much lighter than all other baryons or hadrons present in this world. And the second is deconfinement. So color degrees of freedom are liberated. And these two mechanisms drive the entire phase diagram here. And the most challenging part of it is to understand the mechanism of chiral symmetry breaking and confinement, which is still an unsolved problem. So I will talk today about the chiral symmetry in QCD and not about the aspects of confinement. So in QCD, even with physical quark masses, the light quark masses are much smaller than the intrinsic scale of QCD, which is the lambda QCD. So even when we talk about the physical QCD as 2+1 flavor, it respects an unitary symmetry U2 left cross U2 right to a very good extent. And this is what we call as the two flavor chiral symmetry. Now, one can write these unitary matrices in terms of special unitary matrices. And when we talk about chiral symmetry breaking versus restoration, so the chiral symmetry breaking means that the SU2A part is broken, which leads to pseudo Goldstone modes, which are the pions. And this is the non-singlet part of the chiral symmetry. So when we know the phase transition happens, which is a crossover. I should not tell a phase transition, but it's a smooth crossover. And we know the temperature at which it happens to a very unprecedented accuracy. So we know it up to 1% precision. And I was involved in this work as a postdoc. And then there were some other groups also which confirmed this, value. But when we talk about this temperature, this is the temperature at which the non-singlet part of chiral symmetry is restored, beyond which it is restored. Now, the question that we would like to ask is what happens to the anomalous UA part of this chiral symmetry? When is it effectively restored? Now, why is this question interesting? Because though it is a subgroup of the entire chiral symmetry group, however, the non-singlet part is anomalous because of the chiral anomaly. It is always broken due to quantum effects. So, and from this relation, we can see that this UA1 part is related to the index of the gauge fields, and hence its breaking, the origin of its breaking is topological. And even though it is not a symmetry, exact symmetry, but there has been model quantum field theory studies which share the same symmetries as a two-flavor QCD. And people can tune the amount of UA1 breaking in these models. And it has been shown that the magnitude of this UA1 breaking term in all of these models actually determine what will be the nature of the phase transition, whether it is first order or second order, when in the chiral limit of QCD. Of course, when we switch on the masses, the exact phase transitions become a crossover, but the universality behavior always stays there. The mass dependent corrections always overwhelm that part. But the important point is UA1 part of the chiral symmetry, even though it is anomalous, it affects the nature of phase transition in two-flavor QCD, QCD with two light flavors. And of course, if we can find an answer to this question of how UA1 restoration happens effectively, it will never be exactly restored because it is always broken due to quantum effects. I will discuss what is the meaning of an effective restoration in the next slides. But if we understand the dynamics of these thermodynamics of this UA1 restoration, then we can also understand the topological origin of chiral symmetry breaking, because ultimately we want to understand why these mechanisms are happening from very fundamental perspective. So, as I already mentioned in the last slide, since UA1 is not a symmetry of the partition function, so there is no order parameter to study this. So we usually study it from the properties of hadrons. So whenever hadrons with specific quantum numbers, so what happens here is we look at these two hadrons. This is flavor singlet, flavor. So this is a Dirac scalar, but it has a flavor index, and it belongs to the scalar isotriplet, and this is pion, which is also a flavor isotriplet, as well as it has a gamma 5 index. Whenever these two hadrons or hadronic correlation functions become degenerate, then we actually can tell that UA1 is effectively restored. So this is one of the ways one can study these problems. So one looks at integrated correlation functions of hadrons carrying these quantum numbers, and one has usually people look at the 2-point correlation function of these hadrons, and then whenever these correlation functions become exactly the same, this is the temperature at which the UA1 is effectively restored, and this is how we characterize this. Now, this is a very hard problem because this is a non-perturbative problem, so we have to do it through a non-perturbative regulator. We use lattice QCD, and whenever we do study these problems on lattice QCD, we have to discretize our action. So we have to choose some discretization for the Dirac operator. And most of the known discretization of the Dirac operator preserves only a remnant part of the continuum chiral symmetries, all except one, whichever is computationally more accessible till now. And then that's why it is important to see how well all of the chiral symmetries are actually preserved on the lattice, even after doing all this discretization. So for that, we have Ward identities. So one can study these correlation functions. So this chi is the integrated correlation function of the pion, chi pi, and the chi delta is for the delta meson, which was the scalar isotriplet. And by Ward identity, this, when the chiral symmetry is restored, then this difference between pi minus chi delta is related to the disconnected part of the chiral susceptibility. So here we choose a particular discretization of fermions, which is called the highly improved staggered quarks. And one calculates these two quantities on the left side and the right side. So the open symbols are actually this quantity in the right side, and this should be exactly same when we are in the chiral symmetry restored phase. And what we see is when chiral symmetry is restored, these all merge on top of each other, so we cannot distinguish these points. So the Ward identities are satisfied even with this kind of discretization, and we are varying these numbers. When you go to larger n tau, means we are going closer and closer to the continuum limit. So the agreement becomes much more better when we are near the continuum limit or final lattices. Now we also studied the relation between the topology and the UA1 breaking. So if you look at the Ward identities, then this chi disconnected part of the chiral susceptibility is related to the topological susceptibility, which measures the fluctuation of the topological charge in QCD. And by comparing, we can calculate these two quantities independently and see how well it matches. So that is what we did here in this plot. So this topological susceptibility is given by this green band. The band represents the error when we take the continuum extrapolation. And this red is the disconnected part of the chiral susceptibility multiplied by the light quark mass squared. And all of them are taken to be the 1/4 power. This is studied as a function of temperatures, and these temperatures, you can note that these are in the chiral symmetry restored phase. And we see that these agree very well with each other. And one can also characterize the temperature dependence at very high temperatures beyond 2 times the chiral transition temperature. So beyond 350 MeV, the temperature dependence can be given by the dilute instant on gas predictions. So by this, we can now see that this UA1 breaking has a topological connection. Now, one can also study these correlation functions in terms of the eigenvalues of the Dirac operator. So if one calculates this in the infinite volume limit, one can relate this correlation difference in the correlation function of the pion and delta to the eigenvalue density divided by this quantity, where lambda are the eigenvalues of the Dirac operator. Now we have to do these calculations in finite temperature. In zero temperature, there are various relations relating these eigenvalue densities through chiral perturbation theory. But at finite temperature, very little is known. There has been studies which began 10 years before, or more, little bit more than that. And usually all the calculation goes by assuming that this eigenvalue density, which is a function of the eigenvalue as well as the light quark mass, it is an analytic function in lambda and m square. And then Ward identities, chiral Ward identities are used to derive relations between these correlation functions. And then by studying all of these correlation Ward identities, people have found out that if these assumptions are valid, then if one sees that the eigenvalue density goes as a power of lambda cubed, then this is a necessary condition for the breaking of UA1 to be invisible in correlation functions of the scalar and isoscalar up to 6-point correlation functions. Now the question we want to ask is this eigenvalue spectrum always a polynomial in lambda? Which goes into all of these analytic calculations. Yeah. Lambda is the eigenvalue of the Dirac, QCD Dirac operator. So in general, one can write the eigenvalue density as some constant part, which gives you the intercept here, which is related to the chiral condensate through the Banks-Kasher relation. And then it can have a coefficient which is linear in lambda, quadratic in lambda, and the maximum term we can have is cubic term in lambda, because that is what is predicted from the perturbation theory. We cannot have higher terms than that. And all of these coefficients are functions of temperature and the light quark mass. So here we plot, so I am showing our results, which is the work of my student Ravi. So here we plot the eigenvalue density as a function of the eigenvalue at temperatures which is below the chiral symmetry restoration temperature. So this is in the chiral symmetry broken phase. And these are two lattice spacings. This larger number here corresponds to a final lattice size. So it's more closer to the continuum limit. So what one sees is there's a finite intercept here, and then there's a linearly rising part of the eigenvalue spectrum, which we call as the bulk part. And both of this intercept and the bulk actually has predictions from chiral perturbation theory. And we see that indeed all of these predictions work very well. So the intercept is related to the chiral condensate. And if one extracts this chiral condensate, then one can predict the slope of this bulk part. And this slope goes as the fourth power of the chiral condensate divided by the pion decay constant at 0 temperature. So we find excellent agreement with chiral perturbation theory predictions in the chiral symmetry broken phase. Now what happens when we increase the temperature? This is in the phase where the non-singlet part of chiral symmetry is restored. Then what one sees is as one goes to finer and finer lattice spacings, one sees there is a onset of a small pileup of near zero peaks. And then there is this linearly rising part, which is called the bulk part. And these peaks become more and more prominent at temperatures as we go from below the transition temperature to higher, and then it disappears at very high temperatures. And one can characterize this slope, and the slope has a finite this slope of this straight line has a part which is independent of the mass, so it should survive also in the chiral limit, and this will lead to UA1 breaking. That is one of the interesting results we had. And note that this is still behavior here is still not characterized by lambda cube behavior, which is a necessary condition for UA1 breaking that was derived analytically. So we see that the non-singlet part of chiral symmetry is not immediately restored as soon as the singlet part of the chiral symmetry is not immediately restored whenever the chiral symmetry is restored. So this restoration happens at a different temperature. And now one can also study what happens to the lowest part of the eigenvalue spectrum. So these parts. So below TC, of course, we saw that the eigenvalue spectrum has this peak-like structure, whereas at the higher temperature, it has a more flatter structure. And one can compare with the chiral random matrix theory prediction. This is given with a red line. Of course, the prediction will not match very well because the random matrix calculations are all done in 0 temperature. We are here at finite temperature, and we know that at 145 MeV, always there is some problem with the chiral perturbation theory about the radius of convergence, and there are issues. But still, the agreement is very nice because the peak heights are very well matching. And also, one can compare this lowest part of the eigenvalue spectrum. So here we have deflated the lower part of the spectrum by multiplying with a constant which depends on the chiral condensate. So this is essentially zooming in the small eigenvalue sector very well. And what we see is that at very high temperatures, there are no features. So there is a flat-like structure. Whereas if one goes to a chiral symmetry broken phase, there is an oscillation here, which matches very well with the random matrix theory predictions. some people have also tried to get these predictions from random matrix theory from a model, instanton liquid model. So, but I would not like to go into details of it. But yeah. And then, of course, we can calculate this difference between this correlation function, which is an observable, which can give us an estimate where the UA1 breaking, it gives an idea about how much the UA1 is broken. And then we see that if we calculate this, these are all done in the continuum limit, so there are no lattice artifacts. All of these are taken into account in the systematic errors. And if we do a 1 by t square fit from chiral perturbation theory, then there is a nice fall off, and we can see that at temperatures which is about 1.2 times this chiral transition temperature, which is around 190 MeV, this part is effectively restored. Of course, always the UA1 breaking will be there, but that should come from other sources, and that are much more tiny than this. This is the most dominant source, and this subsides at around 1.2 T. So if we want to interpret our results, so we see that from the hadronic correlation functions, the axial part of the chiral symmetry, or the UA1 part, is restored at 1.5 Tc. And this is the part where the near zero or the small eigenvalues separate out from the bulk parts. And if we visualize quarks as many body states moving in the background of this low energy topological states of gauge fields or the instantons, then one can have a nice interpretation. So at temperatures below the chiral symmetry restoration temperature, the instantons are strongly interacting and provides a very strong disordered potential. And then this is responsible for the linear in lambda dependence for the quark Dirac spectrum. And there is no much temperature dependence, almost similarly behaving at temperatures below this Tc. Whereas, and then of course, this allows us to use random matrix theory to understand the universality class and make some predictions. And this is happening because the potential is disordered. So all the information, it is strongly interacting, but is so disordered, all the details of the potentials are lost, and then the gross features of the eigenvalue spectrum can be understood in terms of the random matrix theory. Of course, one can do much more. So these are the recent works that my student Ravi and Harshit did. So one can look at these eigenvalues more carefully. So there is this small peaks, and then there is a arm that comes here, and then it rises linearly. Now, what happens to this arm? So if one looks at the density profile of these arms, so this is the 10th eigenvalue, which belongs to the arm, whereas these are the bulk modes, which belong to the most right-hand side of the spectrum, on the linearly rising part. So these plots, one has removed. So the difference between these two plots are that the temperature fluctuations have been removed through some procedure for unfolding. And then one can see that all of these intermediate eigenvalues, which fall in the arm, they have a percolating structure. So they are not completely delocalized over the lattice, but they have a percolation-like structure. Whereas all the bulk modes are actually completely delocalized over the lattice, except for small fluctuations, which comes due to thermal fluctuation. Yeah. And then, of course, one can measure the fractal dimensions because it has a fractal-like structure. And these fractal dimensions can be also measured from, this is measured from some techniques which are called the box counting techniques, which Mandelbrot and all pioneered. One can look at these and also compare with something called the inverse participation ratio, P2, which measures how delocalized are the eigenvectors of the Dirac operator. So all of these agree very well for the bulk part. So deep in the bulk part where everything is disordered, these all estimates agree. But in this small region of the arm of the eigenvalue spectrum, where one sees fractal-like structures, this fractal dimensions actually goes close to 2.5, and this can be very well argued from the critical exponents of an O4 model. So O4 symmetry signifies that UA1 is still broken, because the symmetry group can be determined from that, and one can calculate the critical exponents beta and nu. in our O4 model, spin model, which is very well known. If one puts those values, then the fractal dimension comes out to be 2.5 around. And what we measure from our studies is also coming close in this region of. This happens just above when the non-singlet part of chiral symmetry is restored. So to summarize, now we are going towards precision calculations. So we are now able to understand the precise details of the chiral symmetry restoration, how different subgroups are getting restored at what temperatures, and what are the signals that come out from the study of the microscopic features of the Dirac operator. And it is evident that the anomalous singlet part of the chiral symmetry gets effectively restored at a higher temperature than the non-singlet part. So when in the literature we talk about chiral symmetry restoration, that is the non-singlet part, and the temperature quoted is that. But of course, the singlet part gets restored at a higher temperature. And of course, all of these processes involve subtle interplay of many-body interactions among quarks and the disordered due to the gauge fields. And this microscopic origin and its understanding is still a work in progress. Thank you very much.
We are running late. I didn't do anything. Okay, we are running late. What happened? Hello. We'll allow 2 questions. Yes, go ahead.
So when you talk about the U1A restoration,
yeah. So when you talk about U1A restoration, so I guess what it might mean is that when you go, because these are instanton effects, so it's e to the minus 8 pi squared by g squared or something. So when you go to high temperatures, the QCD coupling is becoming smaller. So the anomaly does, like, for example, axion masses also don't become very small at high temperatures, which also in that sense, it's a very qualitatively very different from the restoration of the chiral symmetry, which is like something is getting a web or not. Whereas in the, so I guess there are two physics. Should I understand it like this? That
So
U1A is restored because you're going to a more weakly coupled.
No, that the picture that you told, that is true at higher temperatures.
Yes.
Much higher than 2 TC.
I
or
see.
2 times the transition temperature. What we were asking is what happens in this region where the non-singlet part is just restored, non-singlet part of chiral symmetry, and then UA1 is broken or not. That what we want to study.
so what
And that
I'm
comes
trying
from
to,
this hadron correlation function and not just from the dilute instant.
so I guess what I'm asking, why do you expect the U1A to be restored? Is it because at high temperatures these instantons won't be, because the QCD coupling is becoming smaller? Like maybe it's very naive way of thinking.
So as you said, that is true. Means it is always broken. We always call it as an effective restoration. So
But
effective
if you take G to be very small, it's a very exponentially suppressed.
Yes. So what happens is if you go to higher temperatures, then if one has this kind of dilute instanton gas-like picture, then all of these correlation function that we were studying, they have a very sharp temperature dependence. It drops very sharply. It goes as temperature to the power -8. Whereas what we are studying is when this dominant contribution, which is given by temperature to the -2, that subsides. And of course, that will be taken over at higher temperature by those contributions. So those are the subdominant, which will always be there, but as a background. It will be there till asymptotically high temperature because there will be always some residual instanton fluctuation.
Thank you.
Okay. Are there any other questions? Okay. If there are no questions, we can thank the speaker. Thank you very much.
Hello. Yeah, so participants who have taken the TA form, we request that you submit that in the registration desk outside along with the travel tickets. And if you don't have the printout of the travel tickets, just send me. The email ID is provided over there. So I will print those for you. Just get that done by today. It's a request. Thank you.
We'll break for coffee for 20 minutes. Thank you.
Yeah, so again.
Okay, I guess we can start now. The first talk after this coffee session is by Vasudev Dasgupta. Yeah.
Okay, am I audible? Back? All right. So thanks for having me. It's a pleasure to be back at Math Science. So when I was asked to give a talk here at this meeting, I was wondering what to talk about. And so I chose to talk about proposal for an experiment. I'll tell you more about it. And the reason I chose this is in some ways I thought it aligned with the spirit of this meeting, where we're also remembering Rajaji, and he was a big supporter and champion of INO, which sadly is I think has evaporated in the language of Murthy. But I think the idea, I think the support for an underground science laboratory has not evaporated. So we are still quite enthusiastic, and there is. Okay. So the bubble has evaporated. No, so I think in general there is still a lot of support for underground science lab, from scientifically and administratively, and there are many experiments that would be housed in one of these this underground science lab that is being thought about. So the Mega Science Vision documents also talk about the underground science lab. And this proposal for this experiment, it's a neutrino experiment primarily, but based on a new technology that I'll tell you about, would also presumably be housed in this underground science lab where it to come up. Okay, so and it's a futuristic thing. There are lots of things to be done. So it's not a finished piece of work. So you'll have to forgive me if I don't have answers to every single one of your questions. But let's start. Let's start. So okay, so there are many people working on it. I am not talking in any official capacity. It's just that there is no official collaboration, so to say. A lot of people have just organically come together and they're working on this idea. But let me still mention some of the people involved. So whatever I will tell you is based on a science case white paper that was submitted to DAE. And there are several of us who wrote that paper. Names will come up in a second. There is a published paper on the idea where we focused only on supernova neutrino detection using this experiment. And that's the second reference, the JCAP reference that I mentioned here. And there's ongoing work by several people, but at least two well-organized groups. One, which is called the DAE Task Force. So that involves people from different institutions of the DAE with several people, and I'll name them in a bit. And then there's a study group of TIFR, which is a bit more physics and more physics-oriented group, which again, actually, although it says study group of TIFR, it does involve people from outside TIFR as well. And again, I'll name them. So there's a bunch of people. Let's see. Again, this is not a complete list. So this is part of the DAE task force, which involves people from BARC. And then there are people from the Heavy Water Board. Actually, you don't see the ex-CEO of the Heavy Water Board here on this list, who used to be, in fact, the convener of this task force, Dr. Nayak, but he has retired, and then the next person, Dr. Srivastav, is in charge. And then this is the composition of, or at least at some point of time was the composition of the TIFR study group, which, as you can see, involves people from elsewhere as well. Many of you are here. There are many others. Some of the names you will find if you go and look at the report that got generated about 2 years ago at the underground science lab meeting that happened in TIFR. Okay, so there's a whole bunch of people involved. More names will come up as we go on. That should give you a sense that there are people interested in it. That's all I'm saying. Okay, but now back to physics. See, the basic idea is this. Most neutrino detectors are sensitive to only nu E bar, okay, electron antineutrinos, because of inverse beta decay having the largest cross section. Dune is sensitive to nu E, liquid argon. But in many neutrino observation scenarios, it would be very useful to be sensitive to all neutrino flavors. And the reason is simple. You're often interested in things like oscillations. If you know what your total is, if you can actually measure what your total is, then measuring only a part of it allows you to measure the fraction which is related to survival probability, without any theory input. In the case of solar neutrinos, as we remember, so of course, there was a solar model of Bakal, and then you measured, let's say, the charge current signal or something like that, or the electron scattering signal, and you normalized it with the standard solar model, and you could say that, okay, I'm measuring less or more compared to what I'm expecting. But that's not as convincing as measuring the neutral current at SNO directly, where you say that, see, I don't care about your theory now. Okay, you care about the theory at the level that, okay, sterile neutrinos are not included in the analysis. But if you grant me that there are only three active neutrinos, then the neutral current measurement tells you the total number of neutrinos, the total flux of neutrinos. And then the charge current tells you only the electron neutrino fraction. Take an appropriate ratio, and you have a theory independent measurement of the survival probability. Okay, that's very nice. So we would like to do things like that. We remember that in the case of SNO, that was a very, very important measurement, which in my opinion actually solved the problem. Art MacDonald shared the Nobel Prize for this tremendous feat. So we would like to have something like the SNO detector. It's very sad that the SNO detector did not work for long. So what's the challenge for a SNO-like detector? The problem is that you need both neutrons and protons in your detector in order to do neutral current. Okay, so here, as you're seeing, this is a neutrino. It could be neutrino, antineutrino, any flavor, whatever you like, interacts with a deuteron, and it dissociates into a proton and a neutron. And then this neutron can in principle be captured on something else. It could be another deuteron, or it could be a gadolinium, and you could see some final product. Okay, so that's the chain of things that should occur in your detector when there's a neutrino-induced dissociation of the deuteron. Problem is that this deuteron is, first of all, very, very expensive and usually unavailable. So the Canadians got it on a loan from some agency, and then they had to give it back. The SNO could not hold on to the heavy water. Even if you do have this, there are a few small, I would say, minor challenges. One of them is that this neutron that gets captured on deuteron produces only a small amount of energy. Whereas if you could capture it on something else like gadolinium, that's far more efficient and produces more energy. So you could improve upon that part as well. This was a heavy water-based detector, so basically like Super K, but with heavy water. But that meant that there was a large threshold. So the SNO threshold was 5 MeV for most analysis. The proton remains undetected in this detector, and then there's no spectral information, because all you are doing is just basically counting the number of these neutron captures. So you have the deuteron dissociate, you don't see the proton, and the neutron gets captured into something which gives you a little blob of light, and you count. That's all that you were doing at SNO. But that means that this proton was never seen. Okay? Can we do So first of all, we would like to have heavy water, but we would like to do better than snow. Okay, and here is the opportunity. The opportunity is that in India, we have a lot of heavy water. So the heavy water board, which works under the DAE, actually has a lot of heavy water already because we have all these reactors to take care of. And we won't have to buy this heavy water, hopefully. I mean, DAE can loan this heavy water to one of its, let's say agencies, and then at some point of time it goes back. And not only can India, the Heavy Water Board, make heavy water, we can make organic compounds with deuterium, in them. And it's not doping. All the hydrogen in the organic compound is just completely deuterium. So they can do that. Okay, so that's a big strength. Now we know because of our experience with Super K that gadolinium doping works quite well. Okay, so we could just add some gadolinium to our detector and greatly improve this neutron tagging efficiency. And if we work with a scintillator based detector instead of a heavy water based detector, then these problems go away. So the proton immediately gives you scintillation light. The threshold is expected to come down because scintillators have large light output. And because you are seeing lots of photons per charged particle, you can in fact start reconstructing spectra. Okay. So this is the opportunity that one has. So I'll tell you more about the details of the experiment, but before we proceed, let's have kind of a sense of what the final thing should look like. So we are thinking of something like a kiloton or 2 kiloton sized detector. So let's say the active material is something we would, for now call DLS, so deuterated liquid scintillator, although it could be heavy water inside which we dissolve a water soluble scintillator. Now that's also a possibility. So we have not decided yet, but either way, let's call it DLS, and this is in a tank, and it's surrounded by PMTs inside, some big stainless steel tank with some veto, let's say water veto here or something, and then this is some cavern, electronics, and people above. So that's the idea. So we would need an underground lab, we would need a cavern, all of that. So there's some work that the task force and the study group have undertaken, where some discussion has gone on about what kind of let's say vessel, what kind of active photo detector we would be looking at, and so on and so forth. So these are fairly standard, like no different from what Snow was doing, let's say. So these things are fairly standard. Yes. You mean a veto, like an active veto? So see, I already talked about a passive water veto. Yeah.
You have a passive.
And then there's rock and everything. But if you're doing it at a lower depth, let's say suppose you want to do it at Vizag, which is at about 100 meters or something, you might want to do plastic scintillators on top and then active veto. But again, depends. Yeah. Okay. So this is, if you forget about everything else, scientifically, if you forget about everything else in this talk, this is the slide that you should remember. Okay, this is the slide worth remembering. So what you see here are 4 possible interactions that can happen with deuterium. Nu and nu bar, what this is saying is that it could be any flavor. It's a neutral current channel, small threshold. And you're getting this neutron and the proton in the final state, and the neutrino or the antineutrino just floats by. And for nu E and the nu E bar, in addition, there are charge current interactions that can occur. So this tells you that you can detect nu E's, nu E bars, nu mu, nu tau, nu mu bar, nu tau bar, all of that in a single detector. Okay, this is not true of any other detector that I'm aware of. Okay, so that's really cool. Not only that, for any one of these channels, if you see, The neutrino, of course, stays undetected. The outgoing neutrino is not detected. So that we can't do much about that. Every single one of these has one or more charged particles in the final state, which would be detected in the scintillator because we have very low threshold. And not only that, in most of them, except for I think this new E, there is a neutron in the final state. So you would detect the neutron, tag it using gadolinium. Okay. So you have multiple measurements, you have at least two signals for every single interaction. That would reduce background tremendously. So the usual way of thinking about it is that you have some detector and there's always some background and things are just, clicking, constantly. That's your noise. But having two detectors, two signals that are separated by some well-known time, let's say some 20 microseconds or something, is like having a heartbeat. So instead of having one click, you see a click, click. And that's a very recognizable signature that cannot be faked by background so easily. So you cut down background tremendously. So that's why this is good. Okay. So let's talk about the neutral current part first. So this is what we have in mind. So a neutrino or an antineutrino comes in, hits your deuteron, dissociates it into a proton and the neutron. The proton, because it's charged and in the scintillator, it just immediately dumps all its energy. You can quickly, guess that this proton very heavy. If you're talking about order 10 MeV energy neutrinos, this is very non-relativistic, the outgoing proton. So Bethe-Bloch energy loss rate would tell you 1 over beta square that the energy loss rate for this proton is extremely high, order 10, order 100 MeV per centimeter. So it basically does not leave a track or anything. It just basically dumps all its energy at the spot almost. You don't see a track. But the neutron, it scatters around. And normally it would actually scatter around for quite a bit, and I will give you an estimate. But our idea is that you put some gadolinium, which has a very large neutron capture cross-section, and then it gets captured rather quickly. And I'll tell you why this is useful to do. So why this is useful to do is that you might be a bit worried about secondary interactions. What happens if this neutron, instead of getting captured on a deuteron or whatever, goes and hits another deuteron and dissociates it and sets off a chain reaction? Then the next deuteron breaks, another neutron comes out, which wanders around, hits another deuteron, breaks that, and then your detector starts glowing. You don't want that. So you want the neutron to get captured quickly and not cause further dissociations. So it turns out that's kind of guaranteed. The final state protons lose energy quickly and travel less than a centimeter, as I just told you. But the neutrons undergo the following secondary interactions. It can undergo elastic scattering with whatever nuclei are there. It can be radiatively captured, or it can cause this breakup. And this is a bit dangerous if you don't want your detector to suddenly start glowing. So we computed these things. And what we find is, so x-axis is the kinetic energy of the outgoing neutron, and this is the rate of various interactions. This gray line is the rate of deuterium breakup. Okay. And this red and blue lines are the rates of elastic scattering on deuterium and carbon. So if you start with some 10 MeV outgoing energy, you undergo these elastic scatterings and you go down in kinetic energy like this. Okay. Now, if you did not put the gadolinium, which is this green line, this is the capture on gadolinium cross sections, it was not there, then in order to get degraded, you would have to have many elastic scatterings with the deuteron or the carbon. Okay, and you can compute how many. However, if you put the gadolinium, then it, quickly, degrades its energy by having these elastic scatterings and then gets captured, by the gadolinium. So we can estimate that. And this is the number of elastic scatterings that, about 30 to 35 that you would need in order to get captured. And if there was no gadolinium, this number would be of the order of 3000 instead. So you can then estimate that without gadolinium, this neutron would rattle around for about 20 milliseconds. That's too long. Basically, if you have secondary interactions that occur 20 milliseconds after the primary, you will have overlapping signals and you will get confused. You will not be able to reconstruct the events very well. But with gadolinium, you can reduce this 20 millisecond down to 50 microsecond because 30 instead of 3000. And then it's a true useful heartbeat signal. You don't want your heartbeat to be too long. It should be, just right. And you can tune this by putting gadolinium. Okay, so this is the reason why we put the gadolinium in the detector. Okay, so that's the neutral current. So the neutral current was what? That we have deuterium dissociation because of neutrino or antineutrino of any flavor. And the proton gives you scintillation light. The neutron rattles but gets captured on gadolinium and gives you another little blob of light. The efficiency of neutron capture is certainly affected by how much gadolinium you put in. The time to capture is statistically affected by the concentration, of course, but you don't have too much control. You could change it, of course, by doing funny things like what Snow did. Like they had this bulb which had, I think salt water. There's salt phase where there were the little bulbs where they put the gadolinium. They did not put it. They put gadolinium at some point, or they put gadolinium right in the third phase. Yeah, in the third phase they put. So you could do funny things like have like a little balloon inside your detector, like sequence of balloons which have the gadolinium and not else. So then the gadolinium capture only happens inside those balloons. So there are tricks that you can play, but we haven't explored that yet. Yeah. Okay. So that's as I said, so the proton gives you scintillation, the neutron gets captured and you see light there. And so that's your double signature on neutral currents. Charge currents, you have, of course, is already in addition to the neutral current. So charge current is going to happen for nu E and nu E bar. It's in addition to the neutral current. And here's the cross section. Funny thing is that, even these cross sections we had to recalculate. So it turned out that for deuteron, like Snow had the cross section, they probably had it internally somewhere, but we wanted also the differential cross sections, as a function of direction and so on. And Bhavesh, who was a postdoc at TIFR at the time, Bhavesh Chauhan, who's now faculty at BITS Pilani, he quite bravely first of all, confirmed that whatever was available in the literature was basically correct. There were a few typos which we corrected, and recalculated the cross sections using pi-endless effective field theory. And these are his results. So what you can see as a function of energy of the neutrino or the antineutrino, the cross sections. And two different techniques. One using something called a phenomenological Lagrangian approach, and the other using a pi-endless EFT, and they all more or less agree, and it's fine. Okay, so we computed these cross sections, and not only the total cross sections, but the differential cross sections. These are available in the paper and also in this GitHub page that Bhavesh maintains. Okay, now why do you want to do all this other than just the fun and the giggles of building a new experiment? So it's first of all, it's a new technology, right? So like deuterated scintillator, no one's ever built it at any scale. So that would be nice, but it's not just that you demonstrate some new technology. There is a clear science case for it. One of the important things that you can do, so this is a list of things that you can do, not exhaustive. There are other things. And one of the interesting things that you can do is because you lower your threshold from 5 MeV to 2 MeV, you become sensitive to this region of energy where the solar the solar neutrino survival probability changes from 0.57 to 0.3 or something. I'll show you the plot in a second. And that's the MSW turnover. And so if you can map that out, that would be a much more precise test of MSW physics, which has never been done, and I'll show you more about it in a second. You could become sensitive to the day-night asymmetry of solar neutrinos. There are unique opportunities with supernova neutrinos, and I'll tell you a little bit about it. What I will not tell you here today because of lack of time is that this detector can do everything that a normal scintillator detector does. So dark matter, boosted dark matter, and atmospheric neutrinos at the lower end, and all the things that, for example, Juno will do. This can do, of course, at a slightly smaller scale. So Juno is 20 kiloton. This would be maybe 2 kilotons, but it can do. Okay, and maybe new ideas as well. So let's quickly talk about some of the scientific things that it can do. So here, this is the neutrino energy in MeV 0 to 6. Snow threshold was here at 5 MeV. And this is events per kiloton per year, log scale. This is our computed event spectrum. And in this window between 2 to 5 MeV, already you're seeing about 300 events per kiloton per year. Okay. So let's say 1 kiloton detector in 1 year sees about 300 events. Okay. So with 300 events, you can guess what's the typical uncertainty on your survival probability. It's about 5%, 6%. And that's this point here. So here again, energy now in log axis. This is survival probability. This gray band is the theoretical prediction for the survival probability as a function of energy. It goes from 0.57 at the lowest energies to about 0.3 at the highest energies. And that's because of adiabaticity, breaking down at around 2 to 5 MeV. At lower energies, there are measurements, from importantly like Borexino and other detectors. At high energies, there is of course SNO and SK, and these are mostly the 8 boron neutrinos that give you this measurement. But you see, in between this Borexino PEP result, which has large error bars, of course, and the 8 boron result, actually, there is no data here. Okay. There's no data basically between 1 and whatever, 7 or 8. Okay. So this whole space is completely empty. And this red data point doesn't actually exist. So this is what TLS can provide you. Okay. And now if you see, without this data point, actually we haven't really tested the key part of this theoretical prediction. We've seen the two Platos, but we don't actually measure how it turns over. And that would be a much more precise proof of the LMMSW solution. So one can do that. Okay. Of course, you could discover that, something else is happening in that region, and that would be much more exciting, of course. Okay. You could look at the day-night asymmetry. So the sun shines day and night in neutrinos. In fact, at higher, at higher neutrino energies, let's say above 10 or 12 MeV, you actually see more neutrinos at night than during the day, I guess. So I forget how this is defined. But in any case, as a function of energy, whether you see more neutrinos in the day or night, that changes. It also changes by latitude and other things. But let's say this is being done here at the latitude somewhere in India. I think Indu produced this plot, so she can tell you more about exactly what assumptions went in. But the point is this, that you focus on this red curve, which goes through this computed points, and you can see that day versus night, it changes sign at about 10 MeV. Okay. And because now you have large detector capable of measuring neutrinos at these MeV energies, you could track this. Other detectors haven't quite been able to do this, partly because they are never at this, near equator latitude like India. So the most neutrino detectors are above the tropics or below the tropics, and then this effect becomes much smaller there. And this is not a new idea. This is an idea that has existed, in our community for 2 decades, at least 2.5 decades. And I believe this, this excerpt is from one of the web proceedings from one of the webs that happened here, right? I don't know if this hall was there. Yes, yeah. So this is a pretty historic document, and
I think.
Yeah. Yeah, so this is a very, this is a very old idea, but it's still not been measured. So it's kind of cool if one can measure this. How much time do I have? Minus? Sorry, okay, but I'll finish quickly. I'm almost done. I'm almost done. Okay. Sorry, I didn't get any. Okay, so very quickly. So of course, we don't build a detector just for supernova neutrinos because we can't guarantee that supernova will happen in our galaxy anytime soon. But we are aware that when stars explode, they emit lots of neutrinos. You're, going to see, order 10 to the 3, 10 to the 4 neutrinos in about 10 seconds in any kiloton size detector. These things happen about 1 to 3 times per century. The last one actually in our galaxy was around 1900. This was not seen, but the supernova remnant is now being seen. So we know that this was not seen by eye because it was probably dust obscured. Of course, 87A is much more famous. Everyone knows that it happened outside our galaxy in the LMC. So these things happen, not as often as I guess we would like as neutrino physicists, but very important opportunities because they emit all 6 neutrino flavors. So 3 flavors and their antineutrinos. And this DLS type detector would be amazing because it would detect every single flavor. And so that would be very interesting. And one of the things that I'm showing here is that because the statistics can be pretty high, you can try to do a measurement of the outgoing proton kinetic energy. So the scintillation light that you see, turns out, of course, that the scintillation light is quenched a little bit because this proton dumps all its energy in about 0.1 mm or whatever, 1 mm this length. So the scintillation gets saturated. So the scintillation light is not equal to the kinetic energy. It's only a fraction. But this is something that you can calibrate in the lab, a priori. And so by measuring how much scintillation you are getting, you can back calculate how much kinetic energy it must have had. So you can do all of that. And if you know this calibration reasonably well, you can actually, then predict, you can in fact reconstruct back the original neutrino average energy from the measurement of the outgoing proton kinetic energy, the quenched outgoing proton kinetic energy, and so on. So you can do these measurements. I'm out of time, so let me quickly wrap up. You can actually measure the spectrum of these events, as I told you, because you now know this differential scattering cross section that we computed, and this is the quenching factor. So this is how you do it. Last couple of slides. So this is all a dream because many things have to yet be done. Most importantly, we have to demonstrate the feasibility of this technology on some scale. And one of the things that that has to be done is, first of all, you have to synthesize this deuterated liquid scintillator. That's already a hard step. So before that, we want to try to see if we can just take heavy water, D2O, and put in and put in water soluble scintillator in it and do some of these things. There's purification aspects, safety issues associated with inflammability of the scintillator, structural engineering issues, several other things. Very quick progress report. So synthesis and testing of the lab scintillator, including its fluors and interfacing with the detectors. This is already being done at VRC by these people. The studies on DLS synthesis by chemists at VRC. There is some low background setup and testing of the purity of the D2O that we have been discussing with Vandana at TIFR. The water-based liquid scintillator, closed loop purification, PMT setup. This is being carried out at Brookhaven National Labs by Millen. There is a detector simulation in GANT already, a preliminary one that's being set up by Deepak at Central University. And there are lots of physics studies happening. Many more people are involved. Our main strengths are that we own the heavy water, as DAE. So we have access to that. That's the main thing. That's the reason that no one else can do it. I mean, no one else has access to this heavy water. Geographical location is another thing. That's what allows this day-night asymmetry measurement. And generally the ecosystem, within the DAE with the BRC and others, it just makes it possible for such an experiment to be built. So I'll skip a few slides, including that how this detector actually compares to other ideas in the market. Basically, it does equally well or better. And that's my summary. Okay.
Yeah. Any questions?
This is very interesting to hear about this. So one thing I remember from SNOW was the levels of the radio purity that are required. So those were very stringent already for SNOW. Is it even more so now you're trying to lower the threshold, or can you live with the same sort of tolerances that SNOW had? Not just for the heavy water, but also all the materials that go in, the acrylic, the steel, and everything has to be radio pure.
Yes. So we don't, so quick answer is we don't know, because we would need at least a simulation, in GANT to answer this question quantitatively. And in fact, we wouldn't start by trying to do this 2 to 5 MeV measurement with this lower threshold. I think what we would probably do if this project proceeds in the right way is first we would repeat SNOW. We would have a threshold of 5 MeV and measure neutrinos above it, and then we would slowly reduce threshold with better purification. I think that's the way we would go. We would probably need help from people who have more experience with purification, like maybe the Borexino people even, because they have wrapped up. So yeah, so it's very preliminary. I don't know how to do this.
Okay, thank you.
Yeah.
Hey, yeah.
Yeah, so the question is, can one detect the diffuse supernova neutrino background, I guess?
Yeah.
With 1 or 2 kiloton, I think the size is somewhat too small. Yeah.
So thanks for the nice talk. I'm just curious if we know whether gadolinium compounds are heavy water soluble, because that was the problem in Super K. They had to change the thing, right? Compound. So do we?
Yeah.
Because snow did not use gadolinium.
Yeah. So again, the quick answer is we don't know, but my understanding is that the physical chemistry of water and heavy water are not that different. The only difference is essentially that heavy water is like whatever 2 AMUs more, so it diffuses a bit slower. Okay. Other than that, basically there is no difference in chemistry. So, but then again, that's an expectation. What you would do is you would do small scale tests in a lab before you start putting gadolinium in your detector.
Is it DOH easier?
Didn't quite get it.
Instead of doing D2O, isn't DOH easier? Just from the cost perspective. I mean,
that probably isn't the way one would go. I mean, of course we haven't studied. We should study whatever you. I'm sorry? Yeah. Yeah, D2 is sitting. We have D2O. So it's easiest to start with D2O. What we could do, however, is D2O with increasing amounts of scintillator. So that's an optimization. Eventually, this deuteration of a liquid scintillator, so which is basically some organic compound like linear alkyl benzene. So it's a benzene ring with an alkyl chain, and you replace every hydrogen with a deuterium. That, as I understand, is very hard to do for the alkyl chain, but you can do the replacement on the benzene ring. So C6D6 we have already, but the deuterated version of the alkylated benzene, that's hard. So again, there may be some partial deuteration that is done there.
Okay, thanks.
Right. Yeah, so good afternoon, everyone. I hope I am audible to the last. So thank you. First, thanks to the organizer to giving me this opportunity to talk about my work, which is in collaboration with Sarah Collins, Padmanath, and Sasa Pilosek. So the title of my talk is Exotic Tetraquark in CC Q-bar channels. Here Q-bar is any light quark. So to start with a basic introduction, we have the theory of strong interaction, which is QCD, and this is the Lagrangian QCD. And unlike QED, the force mediator here is gluon, and a special property of this is that here we can have self-interacting gluons, and as a result, at very low energies, the QCD becomes non-perturbative, and one is the QCD. This is the plot of QCD coupling as a function of scale. So as you can see that at low energies, the coupling is very strong, and this is also called as hadronic regime or non-perturbative physics. And at large energies, it is perturbative regime, and this is also called as asymptotic freedom. So the regime that we are interested in is the hadronic regime, and for that we have to use some non-perturbative approaches. And one of the non-perturbative approaches or first principle investigation is lattice QCD. So just a small introduction for hadrons. So the textbook definition is that hadrons are composite subatomic particles made of quarks held together by the strong interaction. And we have some standard hadrons like baryons and mesons. So as an example for baryon is proton, and mesons we have pions and kaons. But recently we have also found some exotic hadrons, which are like tetraquarks, which are like composite objects of 4 quarks. And there are other structures also, example pentaquarks. And in all our calculation, we assume isospin symmetry and only strong interaction is there. So yeah, so this is the summary of hadrons that were discovered at LHC in last 12 years. So on the x-axis, you can see the year of discovery, and this is the center of mass energies and GeVs. So you can see that there are various hadrons that have been discovered. There are like 75 new hadrons that have been discovered. And there is summary of exotic discovered in last 12 years. So you can see that there are like pentaquarks and some tetraquarks, and also this pentaquark that was also discussed by in the morning talk by Jim. So yeah, so of all this exotic hadrons, one of the most one of the most recent and interesting one is this TCC 3875. And this is interesting because this is the longest lived exotic till now. And let's see what are some of the special properties of this TCC. So this was discovered by LHCb as an exotic narrow resonance, and its mass is like 3875 MeV with an electric charge of +1. And this is an isoscalar state with quantum number 1 plus. And it, as I just mentioned, that it is the longest lived exotic discovered till date. Now, if this was the signal that was found in the experiments, and one can see that this was found in the mass distribution of D0, D0 pi plus, and this was found very near to the D star D threshold. So this green line is the D star D threshold. Yeah. So there were many D star D scattering studies, including lattice calculations, to explain this state. And one of the first one where they extracted the scattering amplitude from lattice and also find the pole position was in this reference. And the next potential candidate and thing that I'm interested about is the next potential candidate that could be within the reach of LHCb would be a tetraquark with flavor content CCU bar S bar. So the flavor content of TCC was CCU bar D bar. And if we just replace the D bar with an S bar, so that's what our motivation is. So now, as I just mentioned, that we need non-perturbative approaches. To start with, just a small brief introduction of lattice QCD. So lattice QCD is a non-perturbative gauge invariant regulator for the QCD path integral. And in this, we redefine the theory on discretized Euclidean space-time. And the phase space of the QCD is sampled using important sampling procedures such as Markovitch and Monte Carlo algorithms. Now, an important quantity that one use to measure all these energies is correlation function. So what one does is to devise some operators or interpolators with desired quantum numbers that one want to study, and then they construct these correlators. So if one does the spectral decomposition of these correlators, we can get this form. So you can see that the correlation gets contribution from various different states of that particular operator. So you can see that there are various excited state contribution also. And if one wants to extract the ground state corresponding to that particular operator that we have used, one can take the last time limit. As you can see, at last times, the correlation function varies like this. So here is a plot to show this thing. So in log scale, the correlation function as a function of time varies linearly. And if we plot the slope of this plot, we get a behavior like this. So this is like a falling behavior, and at last times it plateaus. So one can extract the ground state if we fit this region and extract the ground state energies. So that is just for the ground state. But what if we want to go beyond the ground state? So for that, what one can do is to construct to use a basis of operators, not just one operator, but use multiple operators, and to create a correlation matrix out of it. And then one can variationally determine the optimal linear combination of these operators to describe the time evolution of the excited states. And this is also called as variation procedure. And in this one, basically, it's all a generalized eigenvalue problem. Yeah. And once we get all the finite volume energy states, we can construct what is called as finite volume spectrum. So we'll spend some time on this. So this is finite volume spectrum for the TCC, which was taken from the reference that I mentioned earlier. And so here on the x-axis, I have lattice volume, the volume of my box. On the y-axis, I have my center of mass energies in the units of DD star threshold. These black curves are the non-interacting levels, which means if my two particles are not interacting, then what would be their energies? While this circular markers are the energies that we extract from the lattice calculations. So the physics that one is interested in here is that to see the shift of this lattice energies with respect to the non-interacting levels. So if the markers are negatively shifted with respect to the non-interacting levels, then the interaction is attractive. But if it is positively shifted, then the interaction is repulsive. So from this, we can at least expect that whether a bound state could exist or not. And yeah, so this was this is spectrum at 280 MeV per ion mass. And a thing to note here is that these are finite volume energy levels, and associating them with infinite volume physics is not so straightforward. So once we extract the finite volume spectrum, how to extract the infinite volume physics? That's the main question. So in infinite volume scattering, we have continuum of states. If we have two particles of mass m, so we have this continuum of states, scattering states that we will have experiments, and from that we can, I mean, in experiment we can have like extract the cross section, and from that we can also extract the partial wave. Sorry, phase shift. But on lattice, we don't have access to the continuum of states, but what we have are finite volume states. And it's not so trivial to map this thing. And Meine and Testein 1990 gave a theorem that it is not possible to extract the infinite volume physics from just a single finite volume energy spectra. So what's the way around? So Lucier in 1991 devised a relation, which is this relation. I will explain it. And using this relation, one can in some way extract the infinite volume physics from the finite volume spectrum. So what this relation is, so here they are taking a determinant over infinite volume scattering amplitude. So this is infinite volume scattering amplitude, and this is matrix of non-mathematical functions. So Lucier kind of gave a relation which connects the infinite volume physics with the finite volume physics. So if given a finite volume spectrum, you can kind of constrain the infinite volume amplitude. So here K tilde is the infinite volume scattering amplitude, and this is related, and this might look too much technical, but it's not that technical. So the scattering amplitude is related to the transfer matrix in this way. And yeah. So if you use Lucier's relation, then what one can do is to we can use this finite volume spectrum to constrain the amplitude more. But just a single finite volume is not enough to constrain the amplitude in many cases. So what one does is to use various different momentum, left frame momenta, like your box frame momenta, your box is moving. So we can have like box at rest, box at 1. So these are in units of 2 pi by L, since in when we are in finite volume, the momenta is quantized. So this is in units of 2 pi by L square. And if we include more and more momenta, we can constrain the cross section and amplitude more and more. And what we can do is not just consider a single volume, but we can consider multiple volumes, and then we can try to constrain the amplitude more. And yeah. So once the infinite volume scattering matrix is extracted, we can extract various physical quantities from that amplitude. And employing these techniques, the first lattice calculation for TCC was performed at 280 MeV per ion mass, and this was the reference. And the authors in this paper identified the pole singularity in the amplitude, which was found to be linked to the physical state that was found in the experiment. And they examined various Riemann sheets, which is associated with the unitary cut in the amplitude. But that I will show you in the next slide. But the main question is, can we predict existence of any such solutions like TCC-US in the CC U bar S bar quark configuration? And that's what my motivation is. So this is the contour plot of cross section. So these are the two plots for physical sheet. This is the contour plot, and this is the 3D plot, and this is for the unphysical sheet. So you can see that this is the pole that they find, and yeah. So this is the result from the PR paper. Yeah. Now that was for the TCC case. Now we comes to the D star DS star spectrum. So this was the spectrum that we found in our case. Now just from the spectrum, you can see that it is a rich spectrum, and it is a relatively difficult system because it has multiple final two-state meson configurations, and there are also some potential mixture of attractive and repulsive interaction in here. And this is also complicated because this is a coupled channel scattering. So we can look at the spectrum. So here we have again finite volumes. The volume of my box. This A1 plus A1 minus are the finite volume irreducible representation.
And on the y-axis, I have center of mass energy in units of dds star threshold. So here the interesting panel to see is this one, this T1 plus. So these are like, so this irreps are like box quantum numbers or quantum numbers when you have finite volume. So the TCC was found in 1 plus quantum number, and that 1 plus quantum number can be the 1 plus quantum number can be seen in this T1 plus irrep. So if we look at this particular region, so the below one is the DDS star threshold, and the above one is D star DS threshold. And one can see that the DDS star energy levels, the lattice energy levels, are shifted downwards, while the above one are shifted upwards. So this is showing kind of like repulsive thing, and this is showing attractive behavior. And our further analysis showed that this kind of behavior is being shown because of the coupling between the two channels. If there were no couplings, then this energy levels would be almost on top of the non-rotating levels, which would show that there is no interaction. So, so I would say that this is still an ongoing analysis, and the analytic structure of the scattering amplitude across the complex plane is still being investigated. So I won't say to take my results as final right now, but so I will still show you the counter that I have found. So these are various. So since I am talking about a coupled channel scattering and there are multiple channels, there are multiple Riemann sheets as well. Like and this Riemann sheet different correspond to different sign of the DDS star momenta. So in the first sheet, you can see that no such. I mean, here in this plot, we don't see any interesting poles. We did find some interesting poles, but those are not in the immediately physically interesting regimes. So, so this is the summary of my talk. So there is a lot of experimental activity going on in this field, and exciting new hadrons discoveries keeps us motivated and active. As Jim also mentioned in his morning talk. And lattice QCD is one of the powerful non-perturbative first principle approach for studying hadrons. As Professor Murthy just mentioned yesterday that lambda 1405, which was found as a molecule that has molecular nature, which was proposed by Professor Rajashekharan decades ago. And various details on extracting finite volume spectrum were discussed. And I also mentioned the Lucius prescription for infinite volume scattering amplitudes to determine from finite volume spectrum. And I also discussed the results for TCC and ongoing D star, DS star scattering studies. So, thank you.
Questions?
So to extract this poles, how large volumes you have to take, or how final lattices?
So
how sensitive it is to the choice of your volumes?
So actually, this poles that we have extracted are for infinite volume amplitudes itself. So we use the Lucius prescription to extract the infinite volume amplitude, and then we look for pole in the infinite volume amplitudes, not in finite volume.
Yeah, but the finite volume spectrum also you have to do it very fine so that you can resolve all the things on the phase shift curve. You can resolve it very well. So how large volumes you have to take?
So yeah, I mean, of course, if we have large volume, then
Means you have to do a more momentum resolution, I guess.
yeah, we have to use various different. I mean, it's not just a large volume, but we have to take multiple volumes actually, so that we get more levels and more we can constrain, because Lucius relation relate any finite volume to any infinite volume thing.
But can you use an arbitrarily small volume to give this
Then
relation?
actually there would be some finite volume effects. It depends on the what hadron you are studying actually, because then if it is a very large hadron, and then if you are taking very small volumes, then there would be some very large finite volume spectrum. Because actually Lucius said that the finite volume effects are exponentially decaying. So if you are taking very large volumes, then the finite volume effects would be very small for that particular case. So yeah, of course, large volume does help. Yeah.
Thanks.
So just a very basic question. So is CC bar and two light quarks, is that also possible? or-
Yeah, yes. So there are actually, I guess. Yes. I guess here. So this is like exotic, and you can see, I guess, we have some CC bar kind of thing. Right.
No, two light
Yeah,
quarks?
CC bar and QQ bar.
Yeah. And would they be similar properties or very different or what?
I mean, similar in what sense? I mean,
In terms of the masses?
so yeah, I mean, you can, I mean, not sure in terms of masses, but you can see that this pink one are the CC by QQ bar thing, and they are like, yeah.
So where is the state
I
that
don't
you
see-
discussed, in
Sorry?
there?
Sorry?
See, oh, your state is not in here.
This one is this.
Yet to
I
be
mean, so
Okay,
so TCC is here, and TCCU is still not found actually.
okay.
Another question?
Okay.
Thank you.
Yeah. Can you hear me? So now it is 1:45, and I'm supposed to give a talk for 45 minutes. So let's see how well I can do to keep you between your lunch and I'm standing between them. So this talk actually is prepared keeping the younger section of the audience. So I can happily say that the experts can go to sleep, the older section of the audience. Anyway, it's always nice to be back in math science, and especially standing here and giving the talk. It's an honor for me. And also it's very, what should I say, personally touching, because we are always remembering Rajaji moving around and talking to each other. I must at least mention one point that when I needed it maximally, it was Rajaji who gave me moral support and very much encouragement. So I'm always indebted to him. Okay, so we get started. I hope I will convince you at the end of this talk that LHC is always interesting and always exciting. So plan of the talk is I will, because of the younger students, I will introduce what is LHC, etc. Then I have a lean menu compared to the number of physics results that LHC experiments are bringing out, almost 100 papers per year per experiment. So I plan to talk about measurement of the W mass, which is just like a hot cake, very recent one. Then search for multi-Higgs productions, top quark front, what is happening, the entanglement in particular. Then I hope I will have time to talk a little bit about one of the interesting results from heavy ion physics sector from Alice, and another one from LHCb, just to give you an example that what is the breadth of physics that we can do at LHC. And before I conclude, I will just hint upon what is coming next after LHC. So LHC, of course, is an unbelievable pursuit for the unimaginable. So I really believe so, and it is really a very exotic machine, exotic tool what we have, and the amount of physics we can do, for which the amount of effort we can put in, is really fantastic. And mind you, soon after the discovery of W and Z bosons, LHC was planned. A broadband hadron collider machine was planned in 1980s, and finally the first PP collision took place 3 decades after that. So that sort of underlines the effort that goes in. This is a 27-kilometer ring, and 100 or 150 meter below the surface, there lies this LHC machine, the ring, and the experiments which collides protons on photons, or once a year for 1 month or so, lead on lead. Sometimes some other special beams are there, like oxygen or xenon. And India participates in CMS and ALICE experiments. CMS and ATLAS are multipurpose experiments, where ALICE is mainly supposed to do heavy ion physics, looking for gluon plasma signatures. LHCb
was meant to study CP violation effects. But truly speaking, now everybody is able to do many things which was not really planned for, and one could not think of it earlier. We were lucky. Nature was kind to us. So soon after LHC started giving collision, we got the Higgs boson, and that was the first raison d'etre for LHC machine. The second main motivation was the probing physics at the TV energy scale is not yet achieved. Let's hope we will do it in some times. And this LHC is going to stay on here for 2 more decades. So how does the proton and proton collisions takes place at LHC? We are able to do well because of the excellent performance of the LHC machine. What we do is that we collect events, triggered events, but in the data sample, mostly we will have a lot of backgrounds and some signal events, hopefully, which is of our interest. If the signal process rate is very low, we need more amount of integrated luminosity. And of course, we have to combine with the acceptance and efficiency of our selection and analysis before we can go and plot the signal and claim that we can do the statistical analysis and claim for discovery. So you can see that over the years, LHC has given us a lot of data at low energy, 7 and 8 TeV, total integrated luminosity 20. That was run 1. Then we had run 2, 140, and we are into run 3 now, which is officially supposed to finish till end of 2025, but it's very likely that it will go on. And just to give you idea, what is the flux? This flux is the crucial thing here, LDT. Okay, so the LHC, when it was planned several decades back, the maximum luminosity people thought that will be achievable was 1 into 10 to the 34. And long back we have crossed that limit. What it means that we have a lot of data in limited amount of time, but there is a very complex challenge because you can see every 25 nanosecond proton bunches are colliding. Each bunch, there are about 3,000 bunches, you can say. Each bunch contains 10 to the power 11 protons. So when the 2 bunches are colliding, there are more than 1 hard interaction. So we have to disentangle the interaction of our interest from the other ones. And this is a picture of the tracks just nearby the colliding beams, which are giving hits in our silicon tracker. And when the number of pileup events is very low of the order of 10, 12. And today already we are having 65 pileup events. So run 3 will continue. Of course, there is a lot of data and so on and so forth. What are our tools? Our tools actually are multi-messenger. I picked up this jargon from our astroparticle physics colleagues, but it is really a tool to study jets, to study B physics when we have secondary vortex, displaced vortex from the interaction point. And of course, we have to deal with WZ, Higgs, and all heavy particles, which has lifetime of the order of 10 to the power minus 24, 25 seconds. And so we can detect leptons. And we do energy momentum conservation. We apply on the energy momentum conservation rule in the transverse direction, because in the longitudinal direction, we cannot measure the initial state. So then we do the missing transverse energy measurement to interpret whether there was any neutrino produced. If you look at this detector, it's extremely complex, and it's almost 15-20 meter in diameter and about 30 meters in length. There are about 100 million electronic channels ready to take data every 25 nanosecond. So this is the complex detector, and it can detect by using subsystems, each of which is supposed to do a specific job. Like the silicons just at the central, most closest to the interaction point, it tracks the charged particles. Then we have the calorimeter system, which is a destructive measurements. We try to measure the energy deposited by the passing particles. And in the outermost level, we have the muons. Muons don't interact much. So we can afford to measure their bend in their curve due to the magnetic field. We put them around to track their trajectory, and from there we get the momentum. So essentially, you know that analysis starts with just looking at the kinematics of the particles we are detecting. And then from there, developing the various variables and finally extracting the parameters of interest. So we must give obedience to the dividend of collective efforts. And so we achieved much more than we had anticipated. Huge amount of physics harvest, including the Higgs boson discovery, various measurements, search for rare processes and physics beyond the standard model. It is not the latest version of the talk, I think. Anyway, fine. So there has been enormous progress in computing capabilities. Without that, we could not have done the way we have been doing the physics in LHC. And we must say the precision theoretical description of the crucial processes went hand in hand along with the experimental community. Over the years, we have developed extensive understanding of the performance of the experiments. These are all crucial points. And of course, this goes without saying, we have been able to judiciously apply sophisticated machine learning techniques. And why do we want to go for all this? Because as I told you, finally, we are measuring some distribution. Typically, this is energy or momentum, invariant mass, etc. that increases. And so does the probability goes down. So we expect a falling distribution from standard model. If our measurements are lousy, our uncertainties are very fat. So we will not be able to see finer effects, which may be coming due to the presence of new physics. And so we have to be careful, and that is the reason, and we cannot afford to miss a discovery. So that is the reason we are very particular about how we do the analysis, and we need help from everybody. Mind you, LHC is the only approved future high energy physics facility for next few decades. As of today, maybe in a few years' time, we will hear something good. Maybe in 2025 or 2026, we will have some announcement about linear collider if it comes, and still it will be about 10-15 years before it comes. So we must maximize the physics harvest. I start with electroweak physics. So of course, by 2024, we have many milestones to celebrate. And most recent is the discovery of the Braut-Englert Higgs boson particle, which is the unique one, enigmatic particle, and that we achieved in 2012. So electroweak sector has been one of the most successful and well-tested part of the standard model, and precision measurements have guided the discovery of the top quark, Higgs boson, etc., using accurate prediction for electroweak observables. That happened in the LEP era. So in the LEP, we were measuring very accurately Z boson properties, later W boson properties, and because of the radiative corrections, because of the virtual contributions from the top and the Higgs coming into these electroweak calculations, the approximate mass of the top quark was anticipated, and even Higgs was range was brought down. So what we need is that we need to calculate the observables. We need the value for the Z mass, top mass, X mass, etc. Now everything we have. So if we know something very accurately and we try to measure that in the experiment, we can over-constrain the standard model. And as I mentioned here, the precision measurements at the LHC is crucial to get hint about heavier particles not directly accessible now. What is it? Let's say W and Z mass are related. This is known, GF is known, alpha M is known. What is crucial here is the radiative correction. What are the radiative correction? This is through the loops. I have put here only the standard model particle, Higgs, Z, top, etc., etc., but there can be BSM particles as well. So if we are able to calculate this and measure the W mass carefully with precision, we shall be able to get hint only about possible BSM particle or BSM physics. Mind you, how much it gets affected? If we have an uncertainty in top mass about 2.1 GeV, W mass gets affected by about 1.9 GeV. And today already in LHC, we have achieved uncertainty in top mass about 330 MeV out of 173 GeV. Out of 125 GeV, the uncertainty is 110 MeV. So W mass in standard model has an uncertainty of 6 MeV. So we are going to talk mostly about the uncertainty here. And humongous efforts have gone in. LEP measured, of course, mind you, Z mass very well. We cannot achieve that. But what we can achieve is that how do we experimentally control the uncertainties in the measurement of the W? And it's not a trivial job at all. It takes a lot of effort, and that's why you may notice that in the last 10 years, there have been only 4 measurements, and it takes 7-8 years of effort. Most exciting has been in 2022, a result published by CDF and which claimed that it has less than 10 MeV uncertainty, but it went beyond, much beyond the standard model prediction. And today, few days back, last week, we had an announcement from the CMS experiment that it's about 10 MeV and it is still nearer to the standard model expectation. Mind you, there are various issues that the experiments CDF was completed more than a decade back. They were in different experimental situations, different environment. All these have gone into calculating the uncertainties. Here I have just given some of the values to give you some idea where does this systematic uncertainty comes from and the amount of data that has been gone into measuring the CMS value of the MW and the Atlas value. So Atlas used, let me go on here. Two things to notice, how the W is being produced. It's very simple. W plus means UD bar. So in proton-proton collision in tevatron, you have the Ws produced with the same helicity, not the case for LHC, which is colliding protons in both the sides. So there are both equal amount of positive and negative polarization states. And the point is, since you need for W plus a D bar, for W minus you need a U bar, the PDF, the parton density function comes into play, and large PDF induced W polarization uncertainty affects the lepton transverse momentum distribution, which is a Jacobian with a peak at MW by 2. Also, there are C quarks because at LHC energy, C quarks are also equally, not equally, quite a bit energetic, and they do take part in producing WZ, etc., etc. So what we do is that because W, we are looking at the leptonic decay of the W, this neutrino we cannot measure. So we try to measure MTW. Classically, CMS has done something different, I'll just tell you. So MTW is defined by the missing transverse energy, missing transverse momentum, and the transverse momentum of the lepton and the angle between them. And what you do by missing transverse momentum is that you measure the momentum of the lepton and the hadronic recoil. So from there you interpret the value of it. In addition, we have QCD complications, heavy flavor initiated processes, and W plus W minus Z are all produced by different flavor participation. So you cannot just take measurement at Z and then transfer it to the W measurement. And of course, there are large gluon induced W production, which is not the case typically for Z. I'll just give you a few highlights. I'm sorry about so much text. What CMS does is it's a three-dimensional fit, profile likelihood fit, separating out two charged leptons and measuring their transverse momentum and the pseudo rapidity. So there are many things. You can have a look at the slides later. Basically, the idea is that instead of transferring the measurement from the Z region to W region, CMS, since the data has a lot of constraining power because we used a lot of amount of data, it has been used to constrain the PDF from the data itself instead of transferring. And what has been done is also scale of the momentum. So when we measure, we have to really validate it. Before that, we have to really see whether the known resonances are peaking at the same value. So using J psi to muon, that has been done. And then it has been validated by studying upsilon to 1s going to muon and Z to 2 muons. This is just some of the distributions which have been studied. So this bin size does not mean anything to you just now. You can say this is at particular PT value and these are the pseudo rapid distribution of the leptons coming from W plus and W minus. Roughly it is at 40 GeV peaking and very slightly. What we do is a likelihood function which checks the compatibility of data with the Monte Carlo. And by doing this, we had to take care of thousands of bin and thousands of systematic uncertainties or the nuisance parameters. I change gear. Talking about the top quark, of course, is the heaviest one and it's extremely short-lived. So what happens is that it decays before hadronization, but we can still get the information of the spin of the top quark, of the parent top quark by studying the leptons, and it's parity violation maximally, so it retains. And we need to know the top mass very well. Also from there we can estimate the value of the Yukawa coupling. And you can see here is that if we don't put in the W and top mass measurements, our uncertainty is how it will be and how crucially it depends. So this is a MW empty plot. Again, have a look at them later, leisurely. We don't have that. Coming to spin entanglement of top quarks. Entanglement, of course, is a key feature of quantum mechanics. So, but typically what is done in cryptography, etc., that is at a much lower energy. Here we are talking about particles at a relativistic energies. So that is the big thing here. But the problem is challenge of observation of spin entanglement TT-bar system. We cannot control the internal degrees of freedom in the initial state. We can only see the top quarks after it is produced and after it has decayed. So we have to define the phase space properly and then try to find out what is happening. So what it studies is the 2 qubit states of TT bar at the production threshold. That's mostly singlet, j equal to 0. And then that rotational invariance gives us a handle. If one is spin up, another has to be spin down, and so on and so forth. So this is the standard spin density matrix of a 2 qubit system. And what is to be studied is this C. This is the critical one because that corresponds to the spin correlation. And each diagonal element of C corresponds to the spin correlation in a particular direction. So this is a good entanglement marker. So that's what we do. So what we actually do is study the angular distribution, okay? And then we try to find out what is the value of D. And I have presented here only the result from Atlas because recently they published it in Nature. CMS paper is coming up in progress of report in physics. So you can see here when the top mass, let's say 173 GeV. So when the top pair is produced at the threshold without the TT bar system is not boosted, then you have a good way that is below minus 0.3. That's the, so and the significance has been more than 5 sigma compared to the null hypothesis of no entanglement. I want to mention this because this is the heaviest system LHC has produced, or we have been able to observe the heaviest system produced at the LHC. This is the 4-top system. And you can see here that we expected lower significance, but we observed more. So is there something happening there? You can see here, this is our standard model, this standing line is the standard model expectation, and both Atlas and CMS measurements go slightly beyond that. But maybe with time, it will come closer as it has been happening, or maybe it will give us something different. These are only the 3-level diagram. What is important is that this KT, this is the coupling modifier of the Higgs-Yukawa coupling to top. So in case there is more here, there is from new physics contribution is there will be slight excess in the net cross section. So that's why we have to measure it well. There are various other top related processes which have been measured well. This one gives you data by theory, which should be aligned with the value 1. And you can see there are some of the processes which are going beyond it quite a lot, of course, with large amount of error. So one of them is TH. So this process is interesting because you can say that you can have TH final state where TTH coupling is involved. In another diagram, it is HWW coupling is involved. So when you do the interference, is a destructive one, and so it is a very low rate. But in case the relative sign is different than what is assumed in standard model, you will have constructive interference, and then the cross section may be high, and from there you may be able to explain this excess. So that's why these are interesting one, and of course we can from there we can find the relative rather the CP nature of the coupling. Then there is another process, TWZ. Again, you can see this is a standard model prediction and the measurement currently is here. So these are, but the 2 sigma is not really something we should be jumping around. We should be talking about 5 sigma effect, etc. So maybe in the coming days when we have more data, we shall be able to resolve these issues. I change gear again and come to the Higgs physics. So there are a large number of Higgs particles have been produced. It's not that we have been able to catch all of them. Most of them goes away, rather most of them remains undetected because of our limited capabilities. Still, we have been able to measure the signal strength with a precision of 6%. What is signal strength is given by what we observe, what is predicted in standard model, and similarly the ratio in which final state we are observing it. Let's say Higgs going to Z star to 4 lepton, Higgs going to WW star, Higgs going to gamma gamma, etc., etc. Essentially, what we do, we want to study the dynamics of production and decay to understand the properties of so-called newly discovered resonance. So what we do is that we determine the quantum numbers, charge, spin, parity, mass, and width. We check if all the predicted decay channels exist or not, look for indications for anomalous couplings, estimate the shape of the Higgs potential, constrain the trilinear and quartic couplings, and study if the Higgs sector is minimal or an extended one. Of course, there are many other to-do lists. What we must remember is that data is accumulating. So when we have limited amount of data, we do what is called inclusive measurements. We just look at the Higgs decaying to a specific final state. So it's collecting all of that time. That is important to establish a channel because we have to see whether Higgs really couples to charm pair or not. So we need Higgs to CC bar process. We need to establish that. Then when we have more statistics, then we can do differential distribution. Differential distribution means each bin, your statistics is reducing. So you must have some sufficient amount of data so that your statistical uncertainties are below your other uncertainties. Then when you have, and then our model dependence, here we are assuming, because you can see here, we say our signal strength is 2. It's not matching with standard model, but we have already assumed this. On top of it, what we have done is that, if you remember my first master equation, there is a factor number of, when we say the number of observed events, there is something called acceptance that we get from the simulation. And we extend it, the acceptance, beyond our fiducial, because our detector is not 100%, it's not hermetic. So we have to extrapolate it. So all these things come into effect, but we can, what do we do it, that we can give to the world only the fiducial cross-section, not for the full cross-section, so that our dependence on the model is reduced. So that is what has been happening over the time, that we are doing more and more differential studies. So what we have done here is the Higgs production at the LHC and the decays. There are large number of tree-level diagrams. I don't expect you to see, but you can see there are blue and red dots. They correspond to the coupling of the Higgs to the Fermat and the bosons, and whether there is a possibility that at this vertices there are effects from new physics. Say, for example, if it is only top loop, then we call it resolved. If it is effect coming from the higher scale physics, then we call it effective coupling. And then if we try to plot the particle mass with respect to the reduced coupling kappa in the so-called kappa framework, we can see that everything is falling in line. Nothing is going up or down here. Of course, you can see there are the ratios to the standard model. If you magnify, there are some uncertainties, of course. So till now, we have been able to measure the Higgs couplings to the vector bosons W, Z, etc. very well using the run 1 data itself by 2013, 2014. Then came run 2 data, much more statistics. Then we could do Higgs coupling to the Fermats. So we have established that Higgs does couple to top, bottom, charm. Neon, mostly we are getting it. We will soon have the result soon. But lighter one, because the coupling depends on the mass of the Fermat, the rates as the lighter particles we have to detect, the rate goes down. So we need more data. So that will come. So these are the way coupling goes. But overall, we can say properties of the discovered BH particle is compatible with those envisaged for a spin zero boson in the standard model. Measurement of the Higgs self-interaction. We talked about the coupling to bosons, coupling to Fermats. What about coupling to itself? Because Higgs gets its mass due to self-interaction. And how do we describe it? If we expand in perturbation theory in terms of the Higgs field, so you can say this is the mass term, and you have the cubic term and the quartic term. So these couplings actually corresponds to 3 Higgses coming together in one vertex. This corresponds to 4 Higgses coming together in one vertex. That means this will give 2 Higgs in the final state, and this will give 3 Higgses in the final state. So determination of the self-coupling parameter lambda is currently the most important mandate. I think this we have to be convinced about. So in LHC, there are still a lot of unfinished job, even in the edges of standard model. And this is the most important mandate we have to do, because this is extremely important. We need to know the shape of the Higgs potential near the minimum. So we have gone very little till now. So whether it is a red curve or the blue curve, and you know that how this blue curve, if it goes down, etc., the evolution of the universe, all that matters critically. So we must know much better here. And you can see here at LHC, mostly Higgs is produced with the more energetic gluons in the initial. Okay. Gluons in the initial state. And when we talk about dihiggs final state, we have one diagram where you have this trilinear coupling, lambda 3. But you can have two Higgs pair, which is called the box diagram, which does not involve lambda 3, but only the top Yukawa coupling. So all these things you have to take into account. And what is the rate? Rate is very low, 31.1 inverse only, almost 1,000 times smaller than about 45 picobond for the single Higgs production. Shall I shout only? That's enough. My voice is low. Okay, let me continue. So this is one type of diagram where what we call gluon fusion, where there is nothing else other than the di-Higgs system. If we go to the subleading process, that is vector boson fusion process, where the initial quarks each emits a vector boson and then they fuse to produce the Higgs, and finally you have two Higgs in the final state, you have the lambda trilinear coupling. There are two other processes. Look at this third one. This is most important, again, because this is a different type of coupling which cannot be seen in any other processes. So this is two vector bosons coupling to two Higgses. Till now we studied HVV, HFF, but here is a process which is VVHH. So vector boson processes, that's why, are very important. But again, the cross section is very low. Initially we studied just inclusive di-Higgs production, and then slowly we are targeting and trying to do things. But it's yet to be seen. What we are getting is essentially upper limits at the 95% confidence level. So if we look at the di-Higgs, we will be looking, let's say, at the invariant mass, and then you can see at the low values, this is the top threshold. Again, remember 173 GeV. So at the top threshold, this is the diagram. This is the Feynman process, which really contributes more. Then this is the one which dominates. And of course, as it should be, it goes down. Experimentally, we have to resort to some final state. So what are the final states? So we look at what are the final states we can detect in the experiments. That is BB bar, WW going to leptons quite often or hadrons, tau tau, ZZ again going to leptons or the hadrons, and the photons. So you have to combine. One Higgs goes to BB bar, another Higgs goes to WW. So the net branching fraction will be 25%. So you go down like this. But we know already when we were doing single Higgs measurements that diphoton is one of the best channels because of the very high resolution, mass resolution we have. So quite often the initial studies of the di-Higgs pair included BB bar and gamma gamma or WW with gamma gamma, etc., etc. Many studies have been done during last 6, 7, 8 years. So let's say when we are looking at this, we look at M gamma gamma. M gamma gamma, let's say we are looking at MBB gamma gamma. So one of the Higgs, if we plot the invariant mass, it should peak at 125 GeV. That's from the di-Higgs process. But then there is a single Higgs process also. So we have to disentangle. When we try to see this excess, we have to say that we see the background plus the single Higgs production plus the double Higgs production. So again, to know this, we need the precise theoretical predictions. So that's why I said that both the experimental and the theory community goes hand in hand. And you can see various considerations here, so we don't have time now. When we search for this, I just want to present one result. If you remember here, look here, I forgot to mention this. So the coupling modifier, if it is 1 means the coupling is equal to the standard model value. If coupling modifier is 0 means that coupling doesn't even exist in nature. Coupling modifier not equal to 0, not equal to 1 means there is some effect from the higher scale physics. And if we do all these net calculations, then we see that the minimum of the cross section is not falling at 1, it's falling at some other value. And you can see here is the cross section, how it goes with the value of di-Higgs mass with different values of coupling. So all this goes into getting such plot. So this is the standard model value. It's at 1, but the minimum is at 0.2, and this is not even symmetric, the experimental value, because the experimental cuts, the selection efficiencies, the acceptance, that all are folded in. So this is what we get. Now the point is, initially we were doing only the di-Higgs diagram, and we were trying to measure the value of kappa lambda and so on and so forth. Then we realized that even in single Higgs processes, kappa lambda is involved, again through the higher order diagrams. So here are some of the examples. You can see that Higgs self energy, or you have when you have let's say QQH process, etc. Then you have the kappa lambda involved here. When you take into account all of them, your limit becomes better. And by looking at the vector boson fusion process, you can also do the kappa 2 lambda, and it has been already established that yes, HHVV coupling does exist. And here is a plot of kappa 2V versus kappa lambda. And even 4 or 5 years back, people thought that measurement of Higgs self interaction is something to be waited for the HLLHC, which is not going to come until about 2020. But the way things are going, it's really fast, it's really exciting, and it's really interesting. So maybe in a year's time, we will have some good news that yes, we have established di-Higgs production. So just watch out. Search for anomalous self-coupling, maybe I should skip it. So when we're looking at di-Higgs production, and we are saying initial state is mostly dominated by the gluon, there are possibilities in beyond standard model physics. And there are limits. You can have a look at it later. Higgs pair can be produced with an intermediate mass new particle. In different models, you can have them. So that possibility also has been looked at. And currently you can see here, there is a small excess around 1 TeV. Yes, I will finish soon. So one has to really check it, how things are. We don't have time to go for detail, but more the merrier. You already saw there are terms with H4. That means 4 Higgs vortices are coming into picture. So here you have this term now, because in standard model, of course, the value of lambda is 0.13, lambda 3 equal to lambda 4, but nobody says that it will be same as standard model. So we have to measure lambda 3 and lambda 4 independently, but we have to take into account consistently which are the diagrams where all of them appear. So you do all these exercise, and then you can see the sensitivity of the current data is such that kappa lambda 3 will not be varying too much. So these values you can see here, I don't know whether you can read 200, 500, etc. This is assuming if the cross section is 200 times the standard model value, because you know cross section is extremely small, 0.893 femtobarn, 0.0893 femtobarn, triple Higgs production process. So if you have 100 femtobarn inverse, you will get about 9 events. So by no chance you can see it, but again, because of the higher order diagrams, you can interpret it. So this is the game, and the value of kappa lambda 4, of course, is much larger. So initially, people thought that we will do di-Higgs physics. From there, we will measure the kappa lambda. So you can see here, when we do HH only, we have large range of the allowed range for the kappa lambda 4, and a smaller range, of course, from the kappa lambda 3. And when we took 100 times standard model value, let's say, we do for the triple Higgs production, then we do this. But when we do together consistently, our allowed range is much lower. That is right. So then we have to do this. So consistent determination of the Higgs potential require combined measurement of lambda 3 and lambda 4. So again, watch out, these works are in progress. Actually, we worked on di-Higgs production. Now with another student, we are working on triple Higgs production, but I don't want to divulge any more details. So wait for a few more time. So particle production LHC. You know, LHC has measured cross section. What is the inelastic production cross section of PP interaction? Of the order of 80 millibarn. And we are coming down to cross section measurements sub femtobarn. So it's 12, 13 orders of magnitude of cross section, the rates that we are measuring. And this again, data by theory. Some of them are going beyond it, but these have very low values. You can see here. And over the time, we guess these things will be resolved. And here I just give you simple rate, how the bottom quark production rate of inclusive B bar pair is of the order of 500 picobarn. 500 microbond, sorry, 500 microbond. And Higgs, I told you about 45 picobond, etc., etc. Sorry. Of course, we know this. Unfortunately, we have not yet seen. Maybe we will see somewhere, sometimes. So I just want to mention that people are doing other things also. So Atlas ZDC has recently been able to exclude a mass of monopole, production of monopole pairs. What is wrong? There is a sensor somewhere. Okay. Yeah. Anyway, so this is the one. Just remember, what is happening is that it's ultra-peripheral collision of two lead nuclei, means the center of the nucleus of one beam compared to the other one is much more than the twice the radius of the nucleus. So then this is ultra-peripheral, and what you can see here, there will be photon exchanges, and then that will excite the other nucleus, and there will be neutron will be emitted, and there are experimental signatures. So from there you can do this. I should really hurry up. I think this also I have to skip. This is talking about the last one at the LHCb. The latest measurement says it's consistent with the anomalies observed in B2 SMU studies, but it's only 1.4 sigma global deviation of data from the standard model. There are heavy ion experiments. They also take data, not every year, but once in 2 years. And then there are reference PP runs, etc., etc. You can have a look at it later. So there they have been able to do what is called double slit experiment. It's basic one, 2 slits. One point is you look at the vector motion production, which decays, but you don't know due to who released the photon, virtual photon. So there is ambiguity. So then when you see it, you see the amplitude, there is a modulation of cos 2 phi. So that's how you do it. So it's really interesting. Now HLLC. This current run through is going to continue till 2026, most probably, at least middle of 2026. Then there will be a long shutdown of 3 years, and then it will start with the high luminosity run. So we are currently here. We want to go there in 2040s. We means you, of course. I will be up somewhere. And we have to make new detectors, because the detectors also were planned in 1990s. We have been doing some revision, but minor way. Major revisions are coming up, and India will be also playing. So with more time, we will have more powerful analysis techniques, more accurate theoretical tools, and other technological breakthroughs, and of course, new ideas, which we have seen during last 10, 12 years. What fantastic things have been done in the whole LHC industry or enterprise, whatever you can call it. And with more data, we will be able to study rare processes. We shall be able to do multi-differential measurements. We shall be able to explore corners of phase space inaccessible with the limited data volume, which we couldn't do today. So it's really going to be a rich physics in the coming 2 decades. So I just want to mention that in India, various groups are taking part in the deliverable towards the phase 2 upgrade of the CMS experiment. I am mostly involved in the level 1 trigger hardware, and in TIFR we are doing this testing the trigger electronics boards, which really involves high-end FPGA system on chips, high throughput data links. Actually, I am not doing anything. I'm just managing. There are extremely very good electronics engineers. They are doing it. So there are many such things we are involved in parallel to doing the data analysis. So what is next? So if you, this is really the old version. This somehow came twice. So basic idea is this, that HLLC, high luminosity LHC, which is supposed to start in 2029 or 2030s, will continue giving proton-proton collisions till 2040s. That means you can imagine the physics will go until 2050s, but there is of course a need to do precision Higgs physics. It will start maybe with 500 GeV when we cannot study all the processes, but some of the processes like Higgs production in association with vector boson, VH, WH, etc., ZH, etc. And then slowly the linear collider will have increased energy. So we shall be able to do that. And in parallel, there will be something like CPAC coming up and things like that. We will wait in next 1 year's time, hopefully, to have better idea about it. It's 1:30, I should stop now. So I must say this diversity of analysis indicates that the mining of interesting physics will continue for next several decades. So stay tuned, and thank you so much. Sorry, I had to hurry, but there is
Yeah.
no time, so
Yeah.
we couldn't talk that
One
detail.
questions.
No, yes, now what I mean that I had to hurry through
Sure.
the slide for everything.
Right, right, right.
Yes. Okay.
Any urgent question? Then
Yeah, yes, answer. It is not very clear that we can do it directly in the places like CMS and Atlas.
Also noted at this.
But maybe if it is produced along with something else, then by tagging that, because general background is so large, you cannot really disentangle. Yeah. Thank you.
So you showed the double Higgs
Yeah.
plot. I'm not quite sure what the message was. Is it?
Message of double Higgs plot results were that we are able to constrain the value of the kappa lambda. This one.
This one, yeah.
Yeah. So kappa lambda is the modifier
Yeah.
of the coupling strength.
To few tenths of percent, to few tenths, yeah.
And the
So that's to about 50% or something. Is that?
Right. So just now it is, the cross section is above standard model value. That means currently our sensitivity is such that we could have sensed the production of double Higgs sphere production if the cross section were about 3.2 the value of the cell.
Okay.
The single.
It does not include the, no, it is a standard model.
This does not include the single Higgs processes.
Yes, it does. It does.
This.
Yeah. So that's why I argued. So initially, few years back, we were doing only the double Higgs. But now it is realized that we have to take into account consistently. And then the precision also and the sensitivity improves.
So I had one more, but if we are running out of time. So the T Higgs that you showed,
That is also my favorite one. One of my students studied this also for her thesis.
so this is with like a single top kind of thing, but then radiating a TH.
And this view goes, of course, in the forward direction. Quite often we don't even identify it. Basically, this
Okay.
is not TTA. If it is a TTA process, the rate goes the square of the term. But here, because of the two diagrams involved, there is interference term. So the YT or the 40, whatever you say,
So-
that comes in.
So I was wondering about the TBH, that will also be included in this, or is that that is included?
That means there is no one here,
With a B tag. So
yeah.
does that also show
Is
this?
it there?
That is also included in this. Will that also show the uncertain, the discrepancy? No, that alone, will that show the same discrepancy or not? Has not been done, sir. There's not enough statistics for that.
Because quite often you can see from the topology that this part is mostly in the forward direction. And we are capable of identifying a jet and identifying from a digit only if the pseudo rapidity is below 2.5, because the tracker, we have to measure the secondary vortex due to the B meson traveling, B quark traveling for some time. And we need a silicon tracker, and the coverage, the fiducial is such that it's up to eta 2.5, let's say 2.4. So the forward going B jets, we cannot identify as coming from B quarks, forward going jets. So that's why THB cannot be done right now.
I have one more, but I'll ask you.
Yeah, I want him before the top. Thank you.
Thank you very much. Detailed talk.
Thank you so much.
Try to come by.
Yes.
ஆன்ல இருக்கா? இது ஆன்ல தானே இருக்கு. அப்ப இது எதுவும் இல்ல. அப்ப அதை மாத்திரலாம். மேல எடுத்துட்டு வரேன் இது.